Our solar system, though a fascinating and essential chapter, is merely a small part of the vast, intricate story of the cosmos. Beyond the planets, moons, and our sun, a realm filled with unimaginable wonders awaits exploration. From rogue planets drifting aimlessly through the cold void to the relentless, mysterious pull of black holes and the faint shimmer of distant galaxies born in the earliest moments of the universe, the cosmos challenges our very understanding of existence itself. Come with us as we journey into the vast unknown, beyond the familiar bounds of our solar system. Nestled within the far reaches of the Milky Way galaxy, our home, Earth, occupies a rather privileged position. Positioned as the third planet from the Sun, Earth sits at an average distance of about 93 million miles, placing it firmly within the Sun's habitable zone. This Goldilocks zone is neither too hot nor too cold, allowing for the presence of liquid water, a fundamental requirement for life as we know it. Unlike Mercury, which endures scorching heat, or Venus, with its unbearable temperatures and toxic atmosphere, Earth offers a balanced climate that has nurtured life for billions of years. This perfect position not only supports life, but makes Earth a unique and rare jewel within our solar system. Orbiting the Sun, Earth completes one full revolution every 365 days, creating the cycle of seasons that has shaped the evolution of life. Our planet's relationship with the Sun is crucial. This cosmic dance, accompanied by our large, singular moon, makes Earth stand out in the vast sea of planets. When compared to its planetary neighbors, Earth may appear modest in size, ranking as the fifth largest planet in our solar system. It's dwarfed by gas giants like Jupiter and Saturn, whose colossal volumes could engulf Earth over 1,000 times. Even Neptune and Uranus, the ice giants, are far larger. Yet, when compared to Venus and Mars, Earth is significantly more expansive. Venus, our sister planet, has a surface area about 90% of Earth's, while Mars, with a diameter barely half of Earth's, is akin to a smaller sibling in the cosmic family. Despite its modest size, Earth's dynamic and diverse geology is far more complex and captivating than its sheer dimensions suggest. From towering mountain ranges and vast oceans to continents that drift across the globe, Earth is a place of constant change and movement. The shifting of tectonic plates, volcanic eruptions, and the continuous recycling of materials in the planet's crust make Earth not only a dynamic environment, but a place where life can thrive. These geological processes, alongside Earth's atmosphere, create a stable yet ever-evolving environment that supports an incredible variety of life forms. One of Earth's most extraordinary features is its ability to support life, which is a result of a delicate balance of factors that come together in perfect harmony. First, Earth's location in the habitable zone of our solar system allows for liquid water to exist. This simple yet essential molecule is the foundation of life. Water serves as a medium for the complex chemical reactions that make life possible. But water alone isn't enough. Earth's atmosphere, composed primarily of nitrogen, 78%, and oxygen, 21%, creates a breathable environment, unlike the toxic carbon dioxide-rich atmosphere of Venus or the thin, insubstantial atmosphere of Mars. In addition, the ozone layer within Earth's stratosphere protects life by filtering harmful ultraviolet radiation from the sun, allowing for a safe, thriving biosphere. Moreover, Earth's magnetic field, generated by the movement of molten iron in the planet's outer core, extends far into space. This magnetic shield protects our planet from the solar wind, charged particles emitted by the sun that could strip away our atmosphere over time. Without this magnetic field, Earth would likely have been left barren like Mars, which lost much of its atmosphere and became a frozen wasteland. Additionally, Earth's geological processes are crucial for maintaining a stable climate over geological timescales. The carbon-silicate cycle, where carbon is constantly recycled between the atmosphere, oceans, and land, helps regulate the planet's temperature, keeping it within a range that supports life. In comparison to other planets in the solar system, Earth's atmosphere and geology are remarkably unique. While Venus and Mars are dominated by either thick, toxic atmospheres or cold, barren landscapes, Earth has a complex and dynamic environment that is constantly in flux. The interplay between the atmosphere, climate, and geology not only sustains life, but also creates the conditions for biological evolution to occur. For example, volcanic activity observed on the moon Io, Jupiter's fiery moon, provides insight into the geothermal processes that shape Earth and may be common throughout the universe. Additionally, the discovery of ancient riverbeds on Mars hints at the possibility of past liquid water, linking the Martian environment to Earth's own water-rich history. Through the study of Earth's geology, scientists are unlocking the mysteries of other planets and celestial bodies. By examining Earth's diverse features, mountain ranges, riverbeds, and tectonic plates, they draw parallels to rocky planets and moons in our solar system and beyond. For example, meteorites found on Earth, remnants of the early solar system, offer clues about the materials and conditions that led to the formation of planets and moons. Some of these space rocks even contain complex organic molecules, suggesting that the building blocks of life are not exclusive to Earth but may be present throughout the cosmos. Lastly, Earth's resilience to catastrophic events such as asteroid impacts offers clues about how life may adapt or emerge under extreme conditions elsewhere in the universe. Despite occasional asteroid strikes and other global-scale events, Earth has bounced back thanks to its robust systems and interconnected cycles. As we study these processes, we can learn more about how life may one day take root on distant planets or moons. In the end, the story of Earth is not just about our planet, it's a window into the larger narrative of the universe. By understanding the unique features that make Earth habitable, we gain insights into the potential for life elsewhere, in places both near and far. As we look beyond our solar system, the journey is just beginning. But also, as we delve deeper into the workings of the Earth, we uncover the vast interconnected processes that govern the universe at large. It's fascinating to see how Earth's history is intricately linked to the broader cosmic narrative. Earth's magnetic field and atmosphere play vital roles in shaping our world, working together as an invisible shield that protects life from the harshness of outer space. The magnetic field, generated by the movement of molten iron in Earth's outer core, extends far beyond the planet's surface, forming the Earth's magnetosphere. This powerful magnetic shield is crucial because it deflects the solar wind, a constant stream of charged particles emitted by the sun, thereby preventing these particles from stripping away the atmosphere and exposing Earth's surface to intense radiation. During solar storms, when the sun releases a higher flux of charged particles, the magnetosphere's role becomes even more evident. It channels some of these particles toward the poles, creating awe-inspiring natural light displays, auroras, visible in the northern and southern skies. This natural light show is not just a beautiful phenomenon, but a vivid reminder of the dynamic processes at play, protecting life on Earth. In addition to the magnetic field, Earth's atmosphere, a delicate layer of gases that envelops the planet, provides an additional layer of defense. The ozone layer, located in the stratosphere, absorbs the majority of the sun's harmful ultraviolet UV radiation, preventing this deadly radiation from reaching the surface and allowing life to flourish. Furthermore, Earth's atmosphere acts as a thermal blanket. Through the greenhouse effect, it traps heat, helping to maintain a global climate that supports life. This combination of the magnetosphere and the atmosphere creates a perfect balance that ensures Earth remains a habitable oasis in the vast expanse of space. As we continue to explore Earth's unique position in the cosmos, it's essential to recognize the profound influence exerted by its singular natural satellite, the Moon. The Moon, the fifth largest satellite in the solar system, plays a significant role in shaping Earth's natural phenomena. Its gravitational pull is primarily responsible for the rise and fall of ocean tides. This tidal force causes the oceans to bulge both toward and away from the Moon, creating high tides in certain areas and low tides in others. This constant ebb and flow of water affects marine life, coastal ecosystems, and even human maritime activities, playing an indispensable role in shaping life on Earth. Beyond tides, the Moon stabilizes Earth's axial tilt, which directly influences our planet's climate and seasonal changes. Without the Moon's stabilizing gravitational influence, Earth's axial tilt could become erratic, resulting in drastic climate shifts over relatively short geological periods. Additionally, the Moon contributes to Earth's rotational speed, with tidal friction gradually slowing the planet's rotation over time, lengthening the day. The moon's presence has been crucial not only in maintaining Earth's environmental stability, but also in shaping the rhythms of life on our planet. Historically, the moon has captured the imagination of countless generations. It has been a source of scientific curiosity, cultural inspiration, and spiritual significance. From early stargazers to modern astronomers, the moon has been a constant subject of observation and study. Its influence extends beyond the physical realm, becoming an intrinsic part of human culture, folklore, and spiritual life. Observations based on Earth have significantly expanded our understanding of the universe. Since ancient times, humans have looked up to the night sky, tracking the movements of celestial bodies with wonder and awe. This early stargazing laid the foundation for the field of astronomy, leading to groundbreaking discoveries about the nature of the cosmos. The invention of the telescope in the early 17th century marked a monumental turning point in this journey. Pioneering astronomers like Galileo Galilei were able to observe moons orbiting Jupiter and the phases of Venus, providing evidence that Earth was not the center of the universe, a revelation that would forever change our understanding of our place in the cosmos. In this way, the story of Earth, the moon, and the universe is not only one of physical processes and cosmic forces, but also one of discovery, curiosity, and profound interconnectedness. These celestial phenomena continue to inspire and challenge us, encouraging us to look up and ponder the mysteries of the universe as we stand on this fragile yet extraordinary planet. In the centuries that followed, telescopes grew more powerful, unlocking the vast mysteries of the cosmos. Astronomers, with their sharpened tools, could peer deeper into space, studying distant galaxies, nebula, and stars in unprecedented detail. As technology advanced, observatories were strategically placed on high mountains or in remote, arid regions, where Earth's atmosphere is thinnest. This strategic positioning minimizes the distortion caused by air turbulence and reduces light pollution, offering a clearer view of the night sky. From these elevated vantage points, monumental discoveries were made. The recognition of an expanding universe, the detection of dark matter and dark energy, and the identification of exoplanets orbiting distant stars. Furthermore, Earth-based radio telescopes have played a pivotal role in mapping the cosmic microwave background radiation, an essential piece of evidence supporting the Big Bang theory. This radiation is a faint afterglow from the universe's earliest moments, providing astronomers with invaluable insights into the universe's infancy. Meanwhile, observatories equipped with gravitational wave detectors have opened entirely new frontiers, allowing scientists to observe ripples in the fabric of space-time caused by cataclysmic cosmic events, such as black hole collisions. These Earth-based endeavors, when combined with the observations made by space telescopes, offer a more complete understanding of the universe's beauty, complexity, and the many mysteries it holds. One prevalent misconception about our place in the universe is the belief that Earth occupies a unique or central position. This geocentric view, once widely accepted, placed Earth at the center of the universe, with all celestial bodies revolving around it. However, the revolutionary work of figures like Copernicus, Galileo, and Kepler challenged this notion. Copernicus introduced the heliocentric model, revealing that Earth orbits the Sun, a star among billions in the Milky Way galaxy. This discovery shifted the perspective of humanity, suggesting that our planet was not the cosmic centerpiece we once believed it to be. Similarly, the Milky Way, though home to our solar system, is just one of countless galaxies scattered throughout the vast expanse of space, each hosting its own systems of stars and planets. Another common misconception is the tendency to underestimate the sheer size of the universe and overestimate our ability to explore it. While humans have made significant strides in space exploration, sending unmanned probes to the outer planets and studying distant galaxies through telescopes, the universe extends far beyond the limits of our current capabilities. The observable universe alone stretches approximately 93 billion light-years in diameter, filled with mysteries that we are only beginning to unravel. Despite our advances, the vastness of space dwarfs our current reach, and our exploration is still in its infancy. Additionally, there's a growing challenge to the idea that Earth-like planets are exceedingly rare. The discovery of numerous exoplanets in habitable zones around their stars suggests that conditions suitable for life, at least as we understand it, could be more common than once believed. These exoplanets, often discovered through the efforts of space telescopes, have expanded our understanding of where life might exist beyond our planet. The possibilities are increasingly vast, reminding us that we are not alone in the universe. These discoveries invite us to adopt a humble yet curious perspective about Earth's place in the cosmos. Life on Earth, with its incredible diversity and adaptability, serves as a beacon of hope and a source of insight into the potential for life elsewhere in the universe. From extreme environments on our planet, like the acidic, boiling springs of Yellowstone National Park, to the dark, high-pressure depths of the Mariana Trench, life has proven its resilience. Organisms known as extremophiles thrive in conditions once thought uninhabitable, expanding our understanding of what constitutes a habitable environment. These remarkable creatures, from the depths of the ocean to the heart of Earth's crust, survive in environments radically different from the temperate conditions most life forms are accustomed to. In addition, microbial life found deep beneath Earth's surface, in rock formations or undersea vents where sunlight never reaches, raises intriguing possibilities. This underground or underwater life survives on chemical energy rather than relying on sunlight, and suggests that similar forms of life could exist on other planets or moons, surviving in hidden, dark corners of the cosmos. With every new discovery, we are reminded that the universe is not only vast, but full of potential, like waiting for us to continue our exploration and embrace the endless mysteries that lie beyond the stars. The study of extremophiles has dramatically reshaped our understanding of life and its potential existence beyond Earth. These extraordinary organisms, thriving in the harshest of environments, whether it's the extreme cold of the polar ice caps or the scalding heat of hydrothermal vents, have provided critical insights into the resilience of life. By studying these resilient beings, scientists are now probing beneath the surface of Mars, exploring ancient riverbeds and underground water reserves in search of microbial life that could have once flourished on the red planet. Mars, with its history of liquid water, presents a tantalizing possibility for past or even present life forms. But the revelations don't stop there. Furthermore, the discovery of extremophilic organisms capable of surviving the vacuum of space and withstanding intense radiation for extended periods has opened up new doors in the search for life across the cosmos. These organisms, capable of enduring conditions that would be lethal to most forms of Earth-based life, suggest that life may not be confined to our planet. A hypothesis known as panspermia has gained increasing attention. This idea proposes that life, or at least the building blocks of life, could spread between planets and moons via meteorites, traveling vast distances across the universe. This revolutionary concept pushes the boundaries of what we once thought possible, urging us to look at celestial bodies not just as isolated worlds, but as potential recipients or originators of life. By examining the diverse ways life manifests on Earth, scientists have gained a profound understanding of the biochemical basis for life. The fundamental building blocks of life, carbon and water, are not just abundant on Earth, but they appear to be essential for the processes that sustain life. With this knowledge in hand, researchers are better equipped to make informed predictions about where life might be found elsewhere. As the search for life in the universe continues, the focus remains on planets and moons that may have the right conditions: liquid water, chemical building blocks, and energy sources that could support life as we know it. This search has grown more methodical and strategic, with Earth serving as the ultimate guide. The solar system, where this quest for extraterrestrial life unfolds, is a remarkable structure, intricately designed and shaped by the gravitational influence of the Sun, a middle-aged yellow dwarf star that holds nearly 99.8% of the system's total mass. The Sun's gravitational pull maintains a delicate balance, keeping the planets, moons, and other celestial bodies in their orbital dance. At its core, the solar system consists of 8 planets divided into 2 distinct groups: the inner terrestrial planets, Mercury, Venus, Earth, and Mars, and the outer gas giants, Jupiter, Saturn, Uranus, and Neptune. Between these 2 groups lies the asteroid belt, a rocky region teeming with debris, a remnant from the solar system's early days. The terrestrial planets, relatively modest in size, are defined by their rocky surfaces and proximity to the Sun. These worlds, particularly Earth, with its abundant liquid water, have proven to be critical in the ongoing search for life. Farther out, the gas giants Jupiter and Saturn, with their massive atmospheres, offer a stark contrast. These planets are far larger and more massive than their icy counterparts, Uranus and Neptune, which are also gas giants but with a unique composition that sets them apart. Beyond the gas giants, the Kuiper belt stretches across the outer reaches of the solar system, populated by icy bodies and dwarf planets like Pluto. This distant region of the solar system remains a frontier of scientific exploration, home to objects that offer clues about the early solar system's formation. But beyond the Kuiper belt, even more distant realms exist. The hypothetical Oort cloud, an icy sphere of objects orbiting the Sun at an unimaginable distance, marks the outermost boundary of the solar system. It is here that long-period comets, often coming from the farthest reaches of our solar system, are thought to originate. These icy visitors occasionally make their way inward, providing a rare glimpse into the distant reaches of our cosmic neighborhood. Yet, as scientists continue their exploration, the understanding of what constitutes a planet has been challenged and redefined over time. The definition of a planet, once thought to be fixed, has evolved dramatically with our expanding knowledge of the universe. According to the International Astronomical Union, IAU, a celestial body must meet 3 criteria to be classified as a planet within our solar system. It must orbit the Sun, be spherical in shape due to its own gravity, and have cleared its orbit of other debris. This formal definition, established in 2006, marked a significant shift in how we categorize celestial bodies. This redefinition has had profound consequences, particularly for Pluto. Long considered the 9th planet of our solar system after its discovery in 1930, Pluto's reclassification as a dwarf planet stirred considerable debate. Located in the Kuiper belt, Pluto shares its orbital zone with other objects and has not cleared its orbit of these debris, thus failing to meet the IAU's 3rd criterion. As a result, Pluto was demoted, an event that sparked discussions not just about Pluto itself, but about the very nature of planets and the criteria we use to define them. The debate over Pluto's status as a planet is just one example of how our understanding of the universe is continuously evolving. It highlights the need for ongoing research and discussion as we explore the vastness of space, seeking answers to questions that have long eluded us. What constitutes a planet? Could there be other forms of life scattered across the universe? How do the various components of our solar system work together to create the dynamic environment we see today? As we continue to investigate the mysteries of our solar system and beyond, one thing remains certain: our quest to understand the cosmos is far from over. But it was part of a broader effort to categorize the growing number of discovered bodies in a scientifically meaningful way. As telescopes and space probes continue to grow more advanced, revealing ever more about our solar system and beyond, the definitions and classifications we use to understand our cosmic neighborhood are continuously evolving. This ongoing evolution reflects humanity's expanding understanding of the universe, a universe far more complex and dynamic than we once thought possible. The asteroid belt and the Kuiper belt, 2 of the most fascinating regions in our solar system, are treasure troves of information. They offer critical insights into the early solar system and the processes that shaped its formation and evolution. These belts are filled with small bodies, often referred to as minor planets, composed of rock, metal, and ice. These objects orbit the Sun but never manage to coalesce into full-fledged planets. The asteroid belt, located between Mars and Jupiter, contains remnants from the solar system's formation over 4.6 billion years ago. By studying these ancient asteroids, scientists are able to glean vital information about the materials and conditions present in the early solar system. The asteroid belt's diversity is staggering. Asteroids come in a variety of compositions, from the carbon-rich C-types to the metallic M-types and the silicate-rich S-types. Each type of asteroid provides a unique glimpse into the varied building blocks available during planetary formation. The orbits and distribution of these asteroids also offer vital clues about the gravitational influences of nearby planets, particularly Jupiter. Jupiter's immense gravity is believed to have played a pivotal role in preventing these objects from forming a planet of their own, creating a cosmic barrier that has left the asteroid belt a fragmented archive of the solar system's infancy. Beyond the asteroid belt lies the Kuiper belt, a vast region extending beyond Neptune's orbit. The Kuiper belt is home to an astonishing array of icy bodies, including dwarf planets like Pluto. These Kuiper belt objects, KBOs, offer invaluable insights into the outer regions of the solar system. Many of these objects are largely unchanged since the solar system's formation, acting as a deep freeze archive of its early history. Studying KBOs allows scientists to better understand the distribution of different types of material in the early solar system and the processes that led to planetary formation. The Kuiper belt is also thought to be the source of short-period comets, which, when they venture close to the Sun, offer accessible samples of primordial material for scientific study. Some asteroids, too, have played a critical role in our understanding of the solar system's formation. These objects are believed to be the parent bodies of meteorites that have fallen to Earth. When scientists study these meteorites, they are able to analyze the materials from the early solar system directly, providing a crucial link between Earth and the distant past of our cosmic neighborhood. The asteroid and Kuiper belts are more than just remnants of the solar system's formation. They are active fields of study that continue to reveal secrets about the history of our solar system. As we learn more about these belts, we gain valuable insights not only into our own planetary system, but also into the formation and evolution of planetary systems beyond our own. The gas giants, Jupiter, Saturn, Uranus, and Neptune, stand apart from the terrestrial planets, Mercury, Venus, Earth, and Mars, in several fundamental ways. These differences highlight the extraordinary diversity of celestial bodies within our solar system. First and foremost, the compositions of gas giants differ drastically from those of terrestrial planets. Gas giants are composed primarily of hydrogen and helium, with Jupiter and Saturn being the epitome of this classification. Uranus and Neptune, on the other hand, contain higher concentrations of ice, earning them the classification of ice giants. In stark contrast to the rocky and metallic compositions of the terrestrial planets, the gas giants are enormous. All four gas giants are significantly larger and more massive than any of the terrestrial planets, with Jupiter being the largest planet in the solar system. Jupiter's diameter is about 11 times that of Earth. This immense size and mass result in extraordinarily strong gravitational pulls, enabling these planets to host an impressive array of moons and planetary ring systems. These rings and moons are composed of ice, rock, and dust, and they orbit around the gas giants, adding to the complexity of these massive worlds. An equally remarkable feature of the gas giants is the lack of a solid surface. Instead, their visible surfaces consist of dense clouds of gas. If you were to descend into one of these planets, the temperature and pressure would increase dramatically, with the gas gradually transitioning into liquid or even metallic states as you move deeper. This makes the internal structure of the gas giants vastly different from that of terrestrial planets. The magnetic fields of the gas giants are also a point of interest. They are far stronger and more extensive than those of the terrestrial worlds, with Jupiter's magnetic field being the most powerful in the solar system. These strong magnetic fields are the result of the gas giants' rapid rotation rates and the movement of conductive materials within their interiors. Another fascinating characteristic of the gas giants is their atmospheric dynamics. These planets are known for their massive storm systems, such as Jupiter's Great Red Spot, a hurricane-like storm that has raged for centuries, and Neptune's Great Dark Spot. These storms are far more intense and long-lasting than anything found on the terrestrial planets. The distinct band patterns that characterize the gas giants' atmospheres, caused by powerful jet streams, are another hallmark of these dynamic worlds. As we venture through the solar system, it becomes clear that the planets' atmospheres are as diverse as the planets themselves. Venus, Earth's neighboring planet, is shrouded in a thick atmosphere composed primarily of carbon dioxide with clouds of sulfuric acid. This makes Venus a scorching greenhouse hell with surface temperatures that soar above 800 degrees Fahrenheit. In contrast, Mars has a thin atmosphere, 95% of which is carbon dioxide, that fails to retain heat, leading to frigid conditions that can plunge to 195 degrees Fahrenheit at the poles. Jupiter's atmosphere, a vast ocean of hydrogen and helium, is marked by intense storms larger than Earth itself, including the Great Red Spot. These extremes in atmospheric conditions paint a vivid picture of the climatic diversity that exists within our solar system. The moons orbiting the planets in our solar system serve as key pieces in the puzzle of our cosmic understanding. These moons are not just satellites, they are windows into the processes that govern planetary systems. For example, Jupiter's moon Europa is believed to harbor a vast ocean beneath its icy crust, hinting at the tantalizing possibility of extraterrestrial life. Similarly, Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane, providing a glimpse into what Earth-like conditions might look like under different chemical compositions. Furthermore, Neptune's moon Triton, which orbits in the opposite direction to the planet's rotation, challenges our understanding of celestial mechanics and formation theories. These moons, each with their own unique characteristics and mysteries, offer crucial insights into the diverse conditions that may support life and the various outcomes of planetary formation. In recent years, space exploration has been marked by groundbreaking discoveries that have deepened our understanding of the solar system. One of the most significant findings came from Saturn's moon Enceladus, where evidence of water vapor plumes erupting from its south pole hinted at the presence of a subsurface ocean capable of supporting life. This discovery challenges the long-held belief that habitable environments can only exist on the surface of planets. The Parker Solar Probe's daring mission to touch the Sun has also provided unprecedented insights into the Sun's atmosphere, or corona, unraveling the mysteries of solar wind acceleration and the mechanisms behind the heating of the corona. These discoveries, along with the detailed images and data from NASA's New Horizons mission during its flyby of Pluto, have revolutionized our understanding of distant worlds, revealing a complex and dynamic planet with ice mountains, flowing nitrogen glaciers, and a blue atmosphere. These discoveries underscore the dynamic nature of our solar system, showing that it is a place of astonishing variety and complexity, far beyond what was once imagined. The Sun's power and stability, which play a foundational role in orchestrating the rhythm and harmony of our solar system, maintain a delicate balance that keeps the planets, comets, and asteroids in their respective orbits, preventing them from careening into the void of space or colliding with each other. The Sun's energy also drives life on Earth, powering everything from photosynthesis to the formation of auroras on planets with magnetic fields. However, this stability is not eternal. The Sun is halfway through its life cycle, and in about 5 billion years, it will expand into a red giant, dramatically altering the solar system's landscape. This remarkable star has shaped the physical arrangement and climate conditions of the solar system, providing the environment necessary for life to thrive on Earth. Yet, the Sun's power and stability will eventually give way to new phases in the evolution of our solar system, phases that will continue to challenge our understanding of the universe and our place within it, but also serve as the setting for the development of life, marking its influence as both nurturing and transformative. Comets, often described as dirty snowballs made of ice, dust, and rock, play an essential role in understanding the universe. They act as cosmic time capsules, holding vital clues to the solar system's history and the processes that have shaped its formation. These ancient bodies are remnants from the solar nebula, the vast cloud of gas and dust from which the Sun and planets condensed over 5 billion years ago. Carrying pristine materials that predate the formation of the planets, they remain unaltered by the heat and gravitational forces that have reshaped planetary surfaces. By studying comets, scientists gain crucial insights into the original composition of the solar nebula. They can unlock mysteries surrounding the dynamics of early solar system formation, including how essential elements for life, such as water and organic compounds, were delivered to the inner planets, including Earth. Every time a comet ventures into the inner solar system, its ice sublimates, releasing gas and dust that form its tail. This provides researchers with a rare opportunity to analyze these ancient substances, offering a direct link to the conditions that prevailed during the solar system's infancy. Landmark missions like Rosetta, which landed on Comet 67P Churyumov-Gerasimenko, have provided unprecedented close-up views of a comet's nucleus and its chemical composition. These observations are helping to unravel the early conditions of the solar system and offering valuable clues about Earth's origins and the emergence of life. In this way, comets are not merely celestial wanderers, they are integral to understanding the cosmic narrative that binds our entire solar neighborhood. The history of space exploration is marked by several missions that stand as monumental achievements in our quest to explore and understand the solar system. Each has contributed uniquely to our growing body of knowledge. The Voyager 1 and 2 spacecraft, launched in 1977, marked a pivotal moment in space exploration. These spacecraft embarked on grand tours of the outer planets, capturing the first detailed images and sending back data about Jupiter, Saturn, Uranus, and Neptune. Their discoveries, including the active volcanoes on Jupiter's moon Io and the detailed structure of Saturn's rings, have had a profound impact on our understanding of the outer solar system and its complexities. Cassini-Huygens, launched in 1997, dedicated 2 decades to studying Saturn and its moons. This mission provided invaluable insights into the planet's atmosphere, magnetic environment, and ring structures. It also deployed the Huygens probe, which landed on Titan, Saturn's largest moon. This discovery revealed a world strikingly similar to Earth, with rivers, lakes, and seas made of methane and ethane. This raised intriguing possibilities about the existence of life in environments previously thought to be inhospitable. Meanwhile, the Mars rovers, Spirit, Opportunity, and Curiosity have completely transformed our understanding of the Red Planet. By analyzing Martian rocks and soil, they found evidence of water's past presence on Mars, a crucial piece of the puzzle in understanding the planet's climate history and its potential to support life. In 2004, the European Space Agency's Rosetta mission made history by becoming the first to orbit a comet, 67P Churyumov-Gerasimenko. It also deployed a lander on the comet's surface, offering a unique window into the role comets play in our understanding of the early solar system and the origins of water on Earth. These missions represent the cutting-edge efforts in space exploration, each helping to shape our knowledge of where we come from and what possibilities lie beyond Earth. The Milky Way, our galactic home, sports a complex and majestic structure that has captivated astronomers for centuries. At its core lies a bulging center enveloped by a halo, both of which harbor ancient stars, revealing the galaxy's maturity. Surrounding this core is the Milky Way's most defining feature, its spiral arms. These vast lanes of gas, dust, and billions of stars wind outward from the center, painting a picture of dynamic beauty and cosmic activity. These arms are not only home to star formation, but also serve as the galactic nursery where new generations of stars are born, further enriching the galactic tapestry. Through continued exploration and observation, our understanding of the Milky Way's structure and function will continue to expand, offering us deeper insights into the intricate and ever-evolving cosmos we inhabit, but also home to vibrant young stars that light up the swirling patterns of the Milky Way. Around the glowing heart of this galaxy lies a thin, ethereal halo, speckled with globular clusters, tight, spherical groupings of ancient stars that serve as some of the oldest residents of the Milky Way. These stellar clusters, glowing dimly in the vastness of space, hold the secrets of the galaxy's early history. Hidden within this halo, though not easily seen, is the dark matter that shrouds the galaxy, creating the unseen gravitational pull that holds the entire structure together. This invisible matter is the glue, an essential force that binds stars, gas, and dust, giving the galaxy its majestic yet enigmatic beauty. One of the defining features of the Milky Way is the bar-shaped structure that extends from its core. This unique phenomenon, common among spiral galaxies, has sparked recent waves of research, aiming to understand its influence on the galaxy's evolution and dynamics. The shape of this bar suggests that the Milky Way's formation and growth have been dynamic and complex, with constant gravitational interactions between stars, gas, and dark matter. From our vantage point on one of its spiral arms, seeing the full grandeur of the Milky Way's design is a challenge. Despite this, scientists continue their tireless efforts to map and observe the galaxy, peeling back the layers of mystery surrounding it. Each discovery contributes to our understanding of not just our galactic home, but the broader cosmos. In the vast expanse of the universe, the Milky Way stands as a shining example of the diverse array of galaxies that populate space. Classified as a barred spiral galaxy, it shares a similar structure with around 2/3 of all the large galaxies in the observable universe. However, the Milky Way's specific dimensions and properties set it apart, highlighting both its uniqueness and its place within a larger cosmic family. For example, compared to the Andromeda Galaxy, M31, which contains about twice as many stars, the Milky Way is slightly smaller. Yet, both galaxies are considered relatively average in size and luminosity compared to the broader galaxy population, which includes colossal giants like IC 11011, the largest known galaxy, stretching an immense 6 million light-years across. This dwarfs the Milky Way's own size, which spans about 100,000 light-years in diameter. What truly makes the Milky Way stand out is its pronounced spiral arms and the bar-like structure at its center. This gives the galaxy its distinct and dynamic shape, revealing an ongoing history of star formation, stellar evolution, and complex gravitational interactions. This stands in stark contrast to elliptical galaxies, which often appear more featureless and uniform with less active star formation. Irregular galaxies, too, lack the structure and mass seen in spiral galaxies and are generally much smaller. Despite billions of years of evolution, the Milky Way retains its iconic spiral arms, thanks to the constant forces of star birth and gravitational interactions. But as much as the Milky Way is a marvel of stability, it is also a galaxy on the move. In around 4 billion years, the Milky Way is predicted to collide with Andromeda, resulting in a merger that will reshape both galaxies in an event that will forever alter the structure of both. This impending cosmic collision highlights the ever-changing nature of galaxies, emphasizing that nothing in the universe is static. At the heart of the Milky Way lies one of the most intriguing and mysterious objects in the entire cosmos, Sagittarius A, Stray, a supermassive black hole with a mass roughly 4 million times that of the Sun. This black hole exerts a gravitational force that controls the orbits of stars and gas clouds in the center of the galaxy. Despite its massive size, Sagittarius A remains relatively quiet compared to the more active galactic centers found in other galaxies, only flaring up on occasion when it interacts with surrounding matter. The existence of this supermassive black hole was first inferred from the rapid motion of nearby stars, movements that suggested a massive, invisible object influencing their orbits. This was later confirmed through radio and X-ray observations, which revealed the presence of the black hole. Sagittarius A serves as the central pivot of the Milky Way, shaping the galaxy's inner workings. The region surrounding Sagittarius A is a natural laboratory for astronomers, providing a unique environment to study the behavior of black holes and their role in galaxy formation. The extreme tidal forces and relativistic effects in this area are unlike anything we can observe elsewhere in the galaxy. These forces offer invaluable insights into the physics of black holes, their impact on the evolution of galaxies, and their crucial role in the universe's grand cosmic narrative. The supermassive black hole at the Milky Way's core is not just a fascinating celestial object, but an essential piece in understanding how galaxies form, evolve, and interact with the universe around them. It is a reminder that the universe is not a static place, but a constantly shifting, ever-evolving expanse of wonder and discovery, but also of intense scientific inquiry as researchers strive to unlock the deepest secrets of our universe, seeking to understand the origins, behavior, and pivotal role of such majestic cosmic giants in the celestial dance of the stars. Stars, those magnificent beacons in the night sky, are born from the cold, dense cores of molecular clouds, vast expanses of gas and dust scattered across the galaxies. These clouds are teeming with potential, and within their swirling depths, regions of higher density begin to form. Catalyzed by the shockwaves from nearby supernovae, these dense pockets of gas and dust collapse under the force of their own gravity, setting the stage for the miraculous process of star formation. As the collapsing region, known as a protostar, continues to draw in surrounding material, its core begins to heat up, reaching temperatures and pressures so extreme that nuclear fusion is ignited. The fusion of hydrogen into helium releases an immense outflow of energy, creating an opposing force against the inward pull of gravity. This marks the birth of a new star, its light beginning to shine brightly into the cosmos. The star's life cycle is inextricably tied to its mass, dictating the path it will take across the sky. Smaller stars like our Sun enjoy long, stable lives, fusing hydrogen in their cores for billions of years. But eventually, as the hydrogen is exhausted, they enter a red giant phase, expanding and cooling. During this stage, these stars start fusing helium into heavier elements, slowly evolving toward their final forms. As the outer layers are ejected, they leave behind a dense, compact core known as a white dwarf. Over the course of many millennia, this white dwarf cools, gradually fading from view. On the other hand, more massive stars experience much shorter, more tumultuous lives. They burn through their nuclear fuel at a rapid pace, triggering the fusion of heavier and heavier elements, culminating in the creation of iron. Unlike the other elements, iron cannot undergo fusion to release energy, and this causes the star's core to collapse. The ensuing collapse triggers a colossal explosion, known as a supernova, that can outshine entire galaxies. What remains after this catastrophic event depends on the star's mass. A neutron star for those of slightly lower mass, or a black hole for the most massive of stars. The explosive death of a star is not the end, however. It is a critical chapter in the ongoing saga of the universe, enriching the cosmos with the heavy elements that form planets and, eventually, life itself. The death of one star is the beginning of another's life, as the remnants of a star provide the raw materials for the birth of new generations of stars. This cosmic recycling process is woven deeply into the fabric of the universe, ensuring the continuous cycle of creation and destruction that defines the cosmos. The influence of stars extends far beyond their own lives, shaping the very structure of galaxies and enriching the universe with the elements necessary for life. Stars themselves display a dazzling variety, with each type distinguished by unique characteristics such as mass, temperature, luminosity, and lifespan. The Hertzsprung-Russell diagram, a vital tool in astrophysics, classifies stars based on their luminosity and temperature, revealing a spectrum that ranges from the dim, cool stars to the hot, luminous ones. At one end of the spectrum, we find the red dwarfs, small, cool stars with low mass and a reddish hue. These stars are the most abundant in the Milky Way and are known for their longevity, capable of burning their fuel for trillions of years due to their highly efficient fusion processes. Moving up the scale in terms of temperature and luminosity, we encounter the main sequence stars, like our own Sun. These stars fuse hydrogen into helium in their cores and exhibit a range of colors from red to blue-white, each reflecting a different surface temperature. Our Sun, for example, is classified as a yellow dwarf. As stars progress through their life cycle, they may enter the giant and supergiant phases. These stars are larger and more luminous than their main sequence counterparts, yet they are cooler, giving them a distinct red or orange hue. Supergiants, the largest and most massive stars, are among the brightest in the universe, but live fast, burning through their fuel rapidly before meeting their explosive end in a supernova. On the hottest end of the spectrum, we find the rare blue dwarfs and blue giants. These stars boast some of the hottest surfaces in the universe, causing them to emit a striking blue glow. However, their lives are brief, burning through their nuclear fuel at an astonishing rate. In the aftermath of a star's life, its remnants, white dwarfs, neutron stars, or black holes, remain. White dwarfs are the compact remnants of medium-mass stars, incredibly dense and often fading slowly over time. Neutron stars, born from the collapse of massive stars, are some of the densest objects in the universe, with gravity so strong that it warps space itself. Black holes, the most enigmatic of all stellar remnants, have gravitational pulls so strong that nothing, not even light, can escape their grasp. The cycle of star birth and death is a continuous, awe-inspiring process, one that shapes the very fabric of our universe. It reminds us that we are not just stardust, but a part of a much grander cosmic tale, one that stretches across the vast expanse of space and time. Each star that is born, lives, and dies contributes to the ongoing dance of creation that governs our universe. The cosmos is a vast and mysterious place where every star and every celestial body plays a pivotal role in shaping the universe as we know it. Among these stellar giants, there are objects so dense, so powerful that they defy comprehension. While neutron stars, remnants of supernova explosions, hold a mass greater than that of our sun, compressed into a sphere the size of a city, they are not quite massive enough to continue nuclear fusion. This lack of fusion means they exist in a delicate balance, maintaining their dense, almost impenetrable form. Then there are black holes. Formed from the most massive stars, these enigmatic objects possess gravity so strong that not even light can escape their pull. Each type of star, whether it's the dense neutron star or the unyielding black hole, plays an essential role in the grand cosmic dance. Stars nurture life by providing stable warmth to planets, while others seed the universe with the heavy elements forged during their explosive deaths. Their life cycles from birth to death contribute directly to the ongoing evolution of the universe. But how do astronomers measure such vast distances in the immense stretch of space? The task is a monumental one, but through a variety of ingenious methods, they are able to measure the distance between us and faraway stars. One key technique used to measure distance within our Milky Way is parallax, a method that relies on the apparent shift in a star's position when viewed against the backdrop of distant stars. This shift occurs as Earth orbits the Sun, and by measuring this shift precisely, astronomers can calculate distances up to a few thousand light years away using simple geometry. However, parallax can only take us so far. For objects beyond its reach, astronomers turn to standard candles, objects whose intrinsic brightness is well known. Type Ia supernovae, one of the most reliable standard candles, provide a clear measurement of distance. These cataclysmic events occur when a white dwarf star accumulates enough mass from a companion star to trigger a runaway nuclear fusion reaction, briefly outshining entire galaxies. Since the luminosity of Type Ia supernovae is well understood, astronomers can use their apparent brightness to determine their distance from Earth. Another invaluable tool in measuring vast cosmic distances involves Cepheid variable stars. These stars are known for their pulsations, a cycle during which their luminosity varies in a predictable pattern. The period of these pulsations is directly related to the star's intrinsic brightness, allowing astronomers to determine its distance by comparing its apparent brightness with its true luminosity. But the arsenal of tools doesn't end there. Astronomers also use relationships like the Tully-Fisher relation, which links the luminosity of spiral galaxies to their rotation speed, and the Faber-Jackson relation, which connects the luminosity of elliptical galaxies to their stellar velocity dispersion. These techniques allow astronomers to extend their measurements beyond our galaxy, covering extragalactic scales and giving us a broader view of the universe. As technology advances and data from space telescopes continue to pour in, astronomers are constantly refining their methods and expanding our understanding of the structure of the Milky Way and our place within it. These ever-evolving techniques allow us to peek deeper into the heart of the cosmos, unveiling some of its most profound mysteries. Among these mysteries are black holes, objects so enigmatic that they challenge everything we know about physics and the nature of the universe. At the heart of nearly every large galaxy, including our own Milky Way, resides a supermassive black hole. These cosmic giants have an outsized influence on their galaxy's structure and behavior. One of the most significant roles these supermassive black holes play is in galactic nuclei activity. As matter spirals into a black hole, it heats up, emitting vast amounts of radiation before crossing the event horizon. This intense energy release can power the luminous cores of active galaxies, known as quasars or active galactic nuclei, AGN. Some of these AGNs are so bright that they are visible across vast cosmic distances, acting as beacons of energy in the dark expanse of space. The energy emitted by supermassive black holes has the power to influence star formation in their surrounding galaxies. By compressing gas and triggering shock waves, it can spur the birth of new stars. Or conversely, by heating and dispersing the interstellar medium, it can suppress star formation, leading to a galaxy that is devoid of new stellar life. In this endless cycle of birth, death, and rebirth, the intricate relationships between stars, black holes, and galaxies continue to shape the universe, guiding its evolution and unfolding new chapters in the cosmic story. The exploration of these celestial phenomena, powered by innovative techniques and ever-advancing technology, reveals not only the intricate mechanics of space, but also the profound role that each of these cosmic entities plays in the grand scale of existence. The more we understand, the more we realize how deeply interconnected everything is in the vast theater of the universe. Moreover, the gravitational influence exerted by supermassive black holes significantly affects the orbits of stars near the galactic center, creating high velocities and dense stellar environments. This dynamic interaction plays an essential role in the growth of the black hole itself, as well as the evolution of the galactic core. It even contributes to the shaping of the bulge, the dense cluster of stars surrounding the heart of the galaxy. In the grand scheme of galactic mergers and interactions, black holes emerge as crucial players in the final stages of the merging process. As two galaxies collide, their central black holes eventually form a binary system, which ultimately merges into an even more massive black hole. This cataclysmic event sends gravitational waves rippling through the fabric of spacetime, a phenomenon first predicted by Einstein's theory of general relativity and later directly detected by the LIGO and Virgo observatories. Thus, black holes are far from mere cosmic oddities. They are pivotal in shaping the galaxies they inhabit. Their influence extends from the very core of galaxies to their broader structure and evolution, positioning them as key participants in the cosmic ballet of the universe. Dark matter represents one of the most profound mysteries in modern astrophysics. As a hypothetical form of matter that neither emits, absorbs, nor reflects light, it remains invisible, detectable only through its gravitational effects. Despite its invisibility, dark matter is believed to constitute approximately 85% of the total matter in the universe, making it a cornerstone in the structure and evolution of the cosmos. The importance of dark matter lies in its significant gravitational influence. It serves as an invisible scaffold, guiding the formation and clustering of galaxies and galaxy clusters. Without dark matter, the gravitational pull from visible matter alone would be insufficient to form the large-scale structures that we observe in the universe. Dark matter also plays a vital role in shaping the rotation curves of galaxies, or the speed at which stars and gas orbit the centers of their respective galaxies. Observations have revealed that galaxies' outer regions rotate much faster than can be explained by the gravitational effects of visible matter alone. Dark matter provides the additional mass and gravitational force needed to account for these discrepancies. Moreover, dark matter is crucial in the architecture of the cosmic web, a vast network of interconnected filaments of galaxies and dark matter that spans the universe. The distribution of galaxies and galaxy clusters aligns with simulations that incorporate dark matter, offering a fascinating glimpse into the large-scale structure of the cosmos. The search to understand dark matter has also led to groundbreaking advancements in detection methods and technologies. Scientists are conducting direct detection experiments deep underground, shielded from cosmic radiation, while also pursuing indirect detection methods through astronomical observations. Unlocking the true nature of dark matter would revolutionize our understanding of the universe, possibly shedding light on new particles and forces that lie beyond the current standard model of particle physics. In this way, dark matter remains not only a critical component of the universe, but also a fundamental element for understanding the formation, structure, and ultimate fate of galaxies and the cosmos at large. Its elusive nature challenges our perceptions of what the universe is made of, urging us to confront the profound mysteries that remain hidden within the cosmic dark. The Milky Way, our galactic home, is not an isolated island drifting aimlessly through the cosmos. Rather, it is surrounded by a collection of smaller galaxies known as satellite galaxies, which orbit the Milky Way in much the same way that moons orbit a planet. Among the most notable of these companions are the large and small Magellanic Clouds, visible from the southern hemisphere as irregular patches of light. These are dwarf galaxies located about 163,000 and 200,000 light-years away from the Milky Way, respectively, and they represent the brightest and most substantial of the galaxy's satellites. In addition to these well-known companions, there exists a range of lesser-known dwarf galaxies that orbit the Milky Way. Some of these, such as the Sagittarius dwarf elliptical galaxy, are currently being cannibalized by the Milky Way's immense gravitational pull. As they are absorbed, they leave behind trails of stars, offering valuable clues about the dynamics of these interactions. Other dwarf galaxies, like the Draco, Ursa Minor, and Sculptor galaxies, orbit at much greater distances. Their faint, star-filled structures provide critical insights into the nature of dark matter and the processes of galaxy formation and evolution. The recent advent of highly sensitive astronomical surveys has led to the discovery of numerous ultra-faint dwarf galaxies, each containing only a few thousand stars. These galaxies are the most dark matter-dominated objects known to exist and are crucial to understanding the Milky Way's gravitational influence. They offer a unique opportunity to delve deeper into the nature of dark matter and its role in the galaxy's evolution. These satellite galaxies not only enhance our understanding of the mass and gravitational reach of the Milky Way, but also play a significant part in unraveling the mysteries of the universe itself, but also serve as natural laboratories for studying star formation, stellar evolution, and the effects of gravitational interactions across a diverse range of environments. Despite their relatively small sizes and dim appearances, the Milky Way's satellite galaxies hold a crucial role in astrophysical research, offering profound insights into the fundamental workings of the universe. These tiny cosmic companions may appear insignificant at first glance, yet they provide a rich tapestry of data that deepens our understanding of the cosmos in ways we might not have anticipated. The Milky Way, our galactic home, is not a still, passive structure. It moves through the vast expanse of the cosmos at an astonishing speed of around 600 kilometers per second. This breathtaking velocity is not just a random occurrence. It's the result of powerful gravitational forces acting on our galaxy. Within the expansive universe, the Milky Way is being tugged by immense cosmic structures like the Virgo cluster, the Great Attractor, and the Shapley supercluster. These larger gravitational forces have been pulling and shaping our galaxy's path for billions of years, creating a cosmic ballet that continues to this day. This cosmic dance is more than a simple linear journey. It involves intricate rotations as well. As the Milky Way speeds through space, our sun, along with billions of other stars, traces arcs around the galactic center, giving the Milky Way its characteristic spiral structure. The combination of this rotation and motion through space adds layers of complexity to our understanding of both the galaxy and the universe itself. Observing other galaxies is a captivating, almost otherworldly journey that stretches billions of light years beyond our own galaxy. To embark on this journey, astronomers rely on a blend of cutting-edge technology and clever observational methods. They deploy powerful telescopes equipped with highly sensitive cameras and sensors to capture the light emitted by far-off galaxies. These telescopes come in a variety of forms. Some are located on Earth, housed in massive observatories that use mirrors to gather light, while others orbit Earth or venture further into the cosmos to eliminate the distorting effects of Earth's atmosphere. What makes these instruments even more remarkable is their ability to detect not just visible light, but the full spectrum of electromagnetic radiation. This includes radio waves, infrared radiation, ultraviolet light, X-rays, and even gamma rays. Each type of light offers astronomers a unique window into the galactic world. For example, ultraviolet light reveals active star formation, while infrared light shows the distribution of cosmic dust. X-rays and gamma rays can indicate high-energy processes like black hole activity or supernovae. Additionally, astronomers utilize spectroscopy to analyze the light, helping them determine critical details such as the chemical composition, temperature, distance, and motion of distant galaxies. This wealth of information allows us to unravel the life cycle of galaxies, understanding how they evolve, interact with each other, and ultimately their role in the vast cosmic web. The closest galaxies to our Milky Way offer an intriguing glimpse into our cosmic neighborhood, each with its distinct characteristics and histories. The nearest of these is the Canis Major dwarf galaxy, a small galaxy discovered in 2003. Located approximately 25,000 light-years away, it resides within the outer regions of the Milky Way, making it our closest galactic neighbor. However, it is not simply a passive entity. It is currently being pulled apart by the gravitational forces of the Milky Way, adding another layer of dynamism to our local cosmic interactions. Following the Canis Major dwarf galaxy, the Large and Small Magellanic Clouds are the second and third closest galaxies to the Milky Way. These irregular dwarf galaxies, visible from the southern hemisphere, lie around 160,000 and 200,000 light-years away, respectively. Their names pay homage to the famed explorer Ferdinand Magellan, who first documented these celestial wonders during his historic circumnavigation of the Earth. These galaxies, with their distinctive structures and histories, are not only significant in their own right, but also provide essential clues to understanding galaxy formation and the gravitational interactions that shape the universe. The Andromeda Galaxy, an astonishing and nearby cosmic neighbor, lies around 2.5 million light-years away, making it the closest spiral galaxy to our own Milky Way. But this isn't just any peaceful neighbor. Andromeda is on a collision course with us, and in about 4 billion years, these two giants of the universe are expected to collide and merge. This upcoming cosmic collision will reshape the structure of both galaxies in unimaginable ways. It's an event that underscores the unpredictable, dynamic nature of our universe, where galaxies continuously interact, collide, and evolve. In the vastness of space, the concept of intergalactic travel remains both fascinating and distant. Intergalactic travel refers to hypothetical journeys between galaxies, crossing the vast stretches of nearly empty space that separate them. The closest galaxy to the Milky Way is the Canis Major dwarf galaxy, located about 25,000 light-years away. And the Andromeda Galaxy, our nearest spiral neighbor, lies a staggering 2.5 million light-years from us. These distances are so vast that they make the concept of intergalactic travel seem almost absurd with current technology. Even the fastest spacecraft ever built by humanity, the Parker Solar Probe, which reaches speeds of about 700,000 kilometers per hour, would take a mind-boggling 3,000 years to travel just a single light-year. At this pace, traveling to even the closest galaxies would require journeys lasting millions of years, far beyond the capabilities of today's propulsion systems. However, the allure of intergalactic travel remains captivating, especially in the realms of science fiction. Scholars, scientists, and storytellers have long speculated about the possibility of faster-than-light travel. Concepts like warp drives, enabling faster-than-light travel by bending the very fabric of space-time, and wormholes, shortcuts through the cosmos, are frequently explored in both scientific theory and popular media. But these ideas, while thought-provoking, depend on physics that are still far from being fully understood. Moreover, the technologies needed to make them a reality are well beyond our current reach. So while the dream of intergalactic travel stirs the imagination, it remains a speculative venture, one that belongs firmly in the future. The immense distances between galaxies remind us of the vastness of the universe and highlight the limitations of human technology in exploring its farthest reaches. Galaxies themselves, these colossal collections of stars, gas, dust, and dark matter, come in a wide variety of shapes and sizes, each more fascinating than the last. To better understand and categorize this diversity, astronomers have developed a classification system, with the most recognized being the Hubble sequence, introduced by Edwin Hubble in the 1920s. At one end of the Hubble sequence are elliptical galaxies, which range from nearly spherical E0 to more elongated shapes, E7. These galaxies are characterized by a smooth, featureless light distribution, and they tend to harbor older, redder stars. Lacking the gas and dust needed for new star formation, elliptical galaxies are generally more quiescent and less active in their stellar life cycles. On the opposite end of the spectrum are spiral galaxies, like our Milky Way, which are characterized by flat, disc-shaped structures with arms spiraling outward from their central bulges. These spiral arms are regions of active star formation, giving spiral galaxies their distinct bluish hue due to the young, hot stars within. Spiral galaxies are further classified by the tightness of their spiral arms and the size of their central bulge, ranging from tightly wound arms and large bulges to loose arms and smaller bulges. Between elliptical and spiral galaxies lie the lenticular galaxies, designated as S0. These galaxies serve as a transitional form, featuring a prominent central bulge and a disk, but lacking the well-defined spiral arms of the typical spiral galaxies. Each of these galaxy types presents a unique glimpse into the complex and ever-evolving structures that populate our universe. The study of galaxies, their interactions, and their evolution continues to reveal the breathtaking dynamics of the cosmos. But lacking the spiral structure, they contain more ancient stars, much like elliptical galaxies, yet they retain a significant disk component. Finally, irregular galaxies defy the regular shapes of the previous categories. Lacking a distinct form, they are often rich in gas and dust, hosting vigorous star formation. These galaxies can result from gravitational interactions or collisions that have distorted their structure. Besides the Hubble sequence, there are other ways to classify galaxies, including by their activity, such as star formation rate, or their environment, such as isolated galaxies versus those in clusters. As our understanding of galaxies deepens and we discover more exotic and unusual galaxies, astronomers continue to refine these classification schemes. Among the vast sea of galaxies, astronomers have stumbled upon some truly astonishing discoveries that have deepened our understanding of the cosmos and challenged prevailing theories. One of the most surprising findings is the existence of supermassive black holes at the centers of nearly all galaxies, including our own Milky Way. These cosmic behemoths, millions to billions of times the mass of the Sun, influence the evolution of galaxies in profound ways and were not anticipated when the theory of black holes first emerged. Another unexpected discovery was that of ultra-diffuse galaxies, ghostly galaxies that are as large as the Milky Way, but contain only 1/100th to 1,000th of the stars, making them incredibly faint and difficult to detect. Their existence challenges our understanding of galaxy formation and dark matter, as they seem to have far more dark matter in proportion to their luminous matter than expected. Perhaps equally surprising has been the detection of galaxies that appear to be devoid of dark matter altogether. Since dark matter is thought to be the backbone upon which galaxies form, finding galaxies without it calls into question our understanding of galaxy assembly and the nature of dark matter itself. The discovery of the Hubble Ultra Deep Field, UHF, also stands out. By pointing the Hubble Space Telescope at a seemingly empty patch of sky, astronomers were able to detect thousands of galaxies at various stages of evolution, some of which were formed only a few 100 million years after the Big Bang. This discovery provided an unprecedented glimpse into the early universe, revealing galaxies in their infancy and offering clues about the initial stages of galaxy evolution. Lastly, the observation of galaxy collisions and mergers, such as the anticipated merger between the Milky Way and the Andromeda Galaxy, underscores the dynamic and ever-changing nature of the cosmos. These cosmic events serve as a reminder that the universe is in a constant state of flux, with galaxies interacting, evolving, and merging to create new cosmic structures, thus driving the continuing transformation of the vast, mysterious universe. In the vast and uncharted territories of the cosmos, cosmic events like supernova serve as both the architect and the catalyst of the universe. These spectacular phenomena ignite bursts of star formation, reshaping galaxies in profound ways. Their importance goes far beyond the immediate spectacle. They provide invaluable insights into the cosmic forces that continuously mold the universe. As astronomers probe these awe-inspiring events, they unlock secrets that continue to fuel our curiosity, propelling the frontiers of space exploration. This ongoing journey illustrates the incredible richness and diversity of the universe, reaching far beyond our familiar Milky Way. Galaxies, unlike the evenly scattered dots we often imagine, are not dispersed uniformly across space. Instead, they exist in clusters, forming a colossal cosmic web that stretches across the vast, seemingly empty voids of space. This web is not only a breathtaking visual phenomenon, but also a structural masterpiece built on the invisible scaffolding of dark matter. At the smallest scales, we find galaxy groups, some containing only a few members, while others house dozens of gravitationally bound galaxies. One of the most well-known of these groups is the local group, which includes our Milky Way, the Andromeda Galaxy, and about 50 smaller satellite galaxies. These galaxy groups, however, are merely the building blocks of much larger structures known as galaxy clusters. These clusters can be truly enormous, containing hundreds to thousands of galaxies stretched out over millions of light years. A prime example is the Virgo cluster, which sits closest to the Milky Way and is home to more than 1,000 galaxies. These clusters are interconnected by enormous filaments, long, thread-like structures of galaxies and dark matter. These filaments form the cosmic boundaries, marking the edges of vast voids or regions of space nearly devoid of galaxies, creating a sponge-like or web-like structure that spans the entire universe. As we move up in scale, we encounter superclusters, colossal collections of galaxy clusters and groups bound together by vast cosmic filaments. The Milky Way is part of the Laniakea supercluster, which contains tens of thousands of galaxies. The way galaxies are distributed and clustered on such monumental scales is deeply rooted in the universe's earliest moments. The initial fluctuations in the density of matter in the nascent universe were magnified by the gravitational pull of dark matter, giving rise to the large-scale cosmic web. Over billions of years, galaxies evolved within this dark framework, with the gravitational forces between them, combined with the accelerating effects of dark energy, sculpting the filamentary structures we observe today. This intricate web of galaxies offers us a window into understanding the fundamental properties of the universe itself. It reveals the unseen forces, gravity, dark matter, and dark energy, that have shaped cosmic evolution across time. These cosmic structures are more than just magnificent patterns in the sky. They are the remnants of an intricate and complex universe, forever evolving and expanding. Supernovae, the cataclysmic explosions marking the death of massive stars, play a pivotal role in shaping the cosmos. They are the universe's forges, acting as cosmic catalysts for the creation of new elements and, paradoxically, also for the destruction of old ones. A supernova can briefly shine brighter than an entire galaxy, its explosive brilliance visible across vast distances. There are two main types. Type 1, which occur in binary systems when a white star accumulates too much matter from its companion, and Type 2, which result from the collapse of a massive star's core once it has exhausted its nuclear fuel. These supernovae have profound and far-reaching consequences. Most importantly, they are responsible for creating the heavy elements we observe today. While stars themselves fuse lighter elements like hydrogen into helium, it is in the extreme heat and pressure of a supernova explosion that the universe forges elements heavier than iron, including gold, silver, and uranium. These elements are blasted into space, where they eventually become part of future stars, planets, and even life itself. Thus, supernovae not only shape the cosmos in the present, but they also plant the seeds for the future of the universe. Furthermore, supernovae play a crucial role in galactic evolution. The shockwaves produced by these explosions can trigger star formation in nearby clouds of interstellar gas, catalyzing the birth of new stars. However, these same shockwaves can also have a destructive side, sweeping through galaxies and clearing out gas, which can hinder future star formation. This feedback mechanism helps regulate the pace of star creation in galaxies, contributing to the structural development of galaxies over time. Beyond their role in star formation, supernovae also serve as important tools for astronomers. Particularly Type 1Ia supernovae are known for their consistent peak brightness, making them invaluable as standard candles for measuring cosmic distances. Observations of these distant supernovae have provided key evidence supporting the theory of the accelerating expansion of the universe, a discovery that has reshaped our understanding of the cosmos. As we continue to study these cosmic phenomena, we are reminded of the intricate and ever-changing nature of the universe. Through the lens of supernovae and the cosmic web, we gain a deeper understanding of the universe's formation, its ongoing evolution, and its vast, interconnected structure, an endless cycle of birth, death, and rebirth that echoes throughout the cosmos. A monumental discovery that reshaped our understanding of the cosmos emerged from observations of distant supernovae, cataclysmic stellar explosions that not only enrich the universe with the heavy elements essential for life, but also shed light on the force driving the universe's accelerated expansion. This breakthrough, which contributed to the 2011 Nobel Prize in Physics, led to the concept of dark energy, a mysterious and powerful force responsible for pushing galaxies apart. These discoveries illuminate the intricate and awe-inspiring processes that govern the life cycle of stars, the formation of galaxies, and the evolution of the universe itself. Supernovae, the explosive deaths of massive stars, play a pivotal role in shaping the cosmos. The heavy elements produced in these fiery deaths, such as iron, carbon, and oxygen, are scattered into space, seeding new generations of stars, planets, and life. This dynamic interplay between creation and destruction is a fundamental feature of our universe, where the death of one generation of stars gives rise to the birth of new ones. The explosion of a supernova can be seen as a cosmic reset button, seeding the very building blocks that will fuel future star systems, including our own solar system. The influence of supernovae extends beyond the creation of heavy elements. These stellar explosions serve as the ultimate test of a galaxy's evolution. Galaxies, large cosmic structures that house billions of stars, interact and merge in an ongoing, often violent dance driven by gravity. These galactic interactions can dramatically alter the structure of galaxies, triggering bursts of star formation, distorting their shapes, and setting the stage for the next chapter in their evolution. As galaxies collide and merge, they undergo dramatic changes from minor structural deformations to full-blown transformative events. Gravity, the force that binds stars together in galaxies, also pulls them into intricate gravitational dances, where galaxies stretch, twist, and distort as they interact. The most awe-inspiring of these encounters occur during major mergers, cosmic events in which two or more galaxies of comparable size collide, often resulting in the creation of a new combined galaxy. This cataclysmic fusion is driven by intense gravitational forces, which disrupt the galaxy's original structure. During these mergers, gas clouds within the galaxies collide and compress, igniting bursts of star formation. In the aftermath, the newly formed galaxy often settles into a new equilibrium, which may result in a dramatic change in its shape, such as the formation of an elliptical galaxy, or in some cases, the creation of a large disk galaxy. These processes of galactic evolution are complex and fascinating, revealing the dynamic and interconnected nature of the universe. Central to this process is the role of supermassive black holes, found at the centers of many galaxies. These enigmatic objects, with masses millions to billions of times that of the Sun, play a significant role during galaxy mergers. If both galaxies involved in a merger harbor supermassive black holes, they will eventually spiral toward each other, merging into a single, even more massive black hole. This event releases enormous amounts of energy, particularly in the form of gravitational waves, ripples in the fabric of space-time that can be detected across the universe. This cosmic collision, a spectacle of both creation and destruction, highlights the deep interconnection between galactic dynamics and the most mysterious objects in the universe. As these galactic interactions unfold, they shape the morphology, motion, and star formation rates of the galaxies involved. The Milky Way, our home galaxy, is no stranger to such events. In fact, it is on a collision course with the Andromeda galaxy. The two galaxies are expected to merge in about 4 billion years, an event that will reshape both galaxies and likely result in the formation of a new, possibly elliptical galaxy. This future collision is a testament to the ever-evolving nature of the universe, where galaxies are in constant flux, interacting, merging, and giving birth to new forms and structures. Amidst these cosmic events, quasars, or quasi-stellar objects, stand out as some of the most luminous and energetic phenomena known to science. Powered by supermassive black holes at the centers of distant galaxies, quasars emit intense radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. As matter spirals into these black holes, it forms an accretion disk, which is heated to millions of degrees, causing it to emit vast amounts of energy. Quasars serve as cosmic beacons, providing insight into the early universe and allowing us to peer back in time over vast distances. Their study is crucial to understanding the formation and evolution of galaxies, offering glimpses into a universe still in the process of becoming. These extraordinary phenomena are a reminder of the incredible complexity and interconnectedness of the universe. From the explosive deaths of stars to the slow, graceful merging of galaxies, each event is a building block in the grand cosmic story, shaping the universe in ways both profound and mysterious. When the universe was still in its infancy, a vast array of quasars began to form, shining their brilliant lights across the cosmos. These enigmatic celestial objects, seen as they were billions of years ago, serve as time capsules, providing astronomers with a unique glimpse into the early universe. Their light, which has traveled across immense stretches of space, acts as a cosmic probe, revealing hidden secrets about the intervening space. As the light of quasars passes through galaxies and intergalactic gas clouds, it gives scientists valuable information about the distribution of matter in the universe, shedding light on the unseen structures that fill the vast emptiness of space. Moreover, the study of quasars is pivotal to understanding the evolution of galaxies. The relationship between the mass of supermassive black holes, those formidable engines that power quasars, and the characteristics of the galaxies in which they reside suggests that the growth of these black holes is intricately tied to the development of the galaxies themselves. This connection hints at a deep and essential role that quasars, along with their supermassive black hole cores, play in shaping the galaxies we observe. Through these powerful cosmic beacons, scientists are uncovering the processes that have influenced the formation of galaxies throughout the entire history of the universe. Quasars also offer an unparalleled window into the mysteries of physics under extreme conditions. At the heart of each quasar lies a supermassive black hole, surrounded by a turbulent, energetic environment. The processes unfolding near the event horizon of these black holes create extreme gravitational forces and radiation, providing unique laboratories where the laws of physics can be tested in ways that are impossible to replicate on Earth. These environments push the boundaries of our understanding, challenging the very foundations of physics and offering new insights into the forces that govern the universe at its most extreme scales. But the story of quasars is just one chapter in the grand narrative of the cosmos. The universe itself is structured in a complex web-like pattern known as the cosmic web. This vast network stretches across the entire expanse of the universe, connecting galaxies, gas, and dark matter in an intricate dance orchestrated by gravity. The cosmic web is composed of long filaments, threads of matter that stretch across the voids of space, linking dense clusters of galaxies at their intersections. These filaments represent the densest regions of the universe, filled with galaxies, gas, and dark matter, forming the backbone of the cosmic structure. The voids, on the other hand, are vast expanses of emptiness, stretching hundreds of millions of light years across, with few galaxies scattered throughout. They serve as the empty spaces between the filaments, acting as the gaps in the universe's intricate structure. The filaments and clusters of galaxies that define the cosmic web began to form less than 1 billion years after the Big Bang. As the initial irregularities in the distribution of matter, primarily dark matter, collapsed under the force of gravity, the first stars, galaxies, and clusters began to take shape, eventually forming the complex structure we observe today. Dark matter, which accounts for approximately 85% of the universe's total mass, played a crucial role in shaping the cosmic web. Though it is invisible and interacts only through gravity, its influence has been pivotal in determining the distribution of galaxies and the overall structure of the universe. This massive, unseen force continues to exert its influence, guiding the evolution of the cosmic web and shaping the distribution of matter across the cosmos. The cosmic web, as seen through the lens of galaxy surveys and intergalactic gas mappings, provides us with invaluable insights into the nature of the universe. It helps scientists understand the formation and evolution of galaxies, the distribution of dark matter, and the dynamic forces that have sculpted the universe over its 13.8 billion year history. These observations not only reveal the structure of the universe, but also offer glimpses into the larger forces that govern the cosmos by pushing the boundaries of our knowledge and challenging our understanding of the universe's past, present, and future. The Big Bang Theory, the cornerstone of modern cosmology, offers a framework for understanding the universe's origin and evolution. According to this theory, the universe began around 13.8 billion years ago from an infinitely hot and dense state, expanding rapidly in a cataclysmic event. This event was not an explosion in the traditional sense, but rather the rapid expansion of space itself, marking the beginning of the universe as we know it. Since then, the universe has been expanding and cooling, leading to the formation of galaxies, stars, and the intricate structures that define the cosmos today. Through the study of quasars and the cosmic web, we are unraveling the mysteries of the universe, piece by piece, one discovery at a time. But rather, the rapid expansion of space itself propelled matter and energy outward in the very first moments following the Big Bang. The universe began as an unimaginably hot and dense point, an infinitely small singularity. As it expanded, the temperature and density began to decrease, enabling the formation of the first fundamental particles such as quarks and electrons. Within minutes, these particles combined to form protons and neutrons, marking the birth of the universe's earliest atomic nuclei in a process known as nucleosynthesis. Over the course of hundreds of thousands of years, the universe continued to cool and expand. As it did, atoms began to form when electrons were captured by nuclei, leading to the creation of neutral atoms. This pivotal era, known as recombination, had profound consequences, as it allowed light to travel freely for the first time. The release of this light, known as the cosmic microwave background radiation, CMBR, offered an enduring snapshot of the infant universe, a faint glow that still permeates the cosmos today. The Big Bang theory is solidly supported by multiple lines of observational evidence. One of the strongest pieces of evidence is the CMBR itself, which was accidentally discovered in 1965. This discovery revealed a uniform, low-energy radiation field that can be detected in all directions across space. The theory also finds further support in the observed redshift of distant galaxies, which shows they are receding from us, a clear indication of the universe's ongoing expansion. Additionally, the relative proportions of light elements like hydrogen, helium, and lithium match predictions from nuclear synthesis, providing further confirmation of the Big Bang's validity. As decades passed, the Big Bang theory was refined through new observations and advancements in our understanding of the universe. Still, it remains the best explanation for both the origins and large-scale structure of the universe. However, it continues to evolve with ongoing astronomical discoveries, enriching our understanding of the cosmos. Approximately 13.8 billion years ago, the universe began its remarkable journey from a hot, dense point to the vast, complex structure we observe today. In the immediate aftermath of the Big Bang, conditions were so extreme that particles and antiparticles were being constantly created and annihilated. The universe then cooled enough for the first stable particles, like quarks and electrons, to form. Over the next few minutes, these particles coalesced into protons and neutrons, eventually laying the foundation for the atomic nuclei that would emerge during nucleosynthesis. Yet, it would take hundreds of thousands of years for the universe to cool sufficiently for electrons to combine with nuclei, forming neutral atoms. This era, known as recombination, marked a transformative moment in the universe's history. For the first time, the universe became transparent to light, allowing photons to travel freely through space. The release of these photons created the CMBR, which serves as a crucial record of the universe's early state. Following recombination, the universe entered what is referred to as the cosmic dark ages. During this time, the universe was mostly filled with hydrogen and helium gas, and there was little visible light. However, gravitational forces began to pull regions of denser matter together, ultimately giving rise to the first stars and galaxies. These initial stars, along with the energy they emitted, ended the cosmic dark ages, transforming the surrounding gas and allowing the universe to once again be illuminated. This era marked the beginning of reionization, when the universe's first generation of stars ionized the surrounding gas, making it transparent to light once again. Over billions of years, stars and galaxies continued to form, evolve, and collide, with larger structures such as galaxy groups, clusters, and superclusters emerging from the gravitational interactions between galaxies. These colossal structures now form the intricate cosmic web that defines the large-scale structure of the universe. Within galaxies, heavier elements were created in the hearts of stars through nuclear fusion and were spread across the cosmos in supernova explosions. These elements seeded the universe with the building blocks necessary for the formation of planets and, eventually, life. The universe continues to expand and cool, driven by the mysterious force of dark energy. This force influences the large-scale structure of the universe, further shaping its evolution. From the first moments after the Big Bang to the formation of stars, galaxies, and beyond, the universe has undergone a remarkable transformation, evolving from a uniform soup of particles to a rich, complex tapestry of cosmic structures. These structures host an incredible diversity of celestial objects, phenomena, and mysteries that continue to unfold. The cosmic microwave background radiation, CMBR, is a faint glow of light that fills the universe, providing a snapshot of the cosmos as it appeared about 380,000 years after the Big Bang. This relic radiation marks the point when photons were first able to travel freely through space, and it is the afterglow of the universe's formation. The CMBR offers invaluable insight into the early universe, allowing astronomers to study the conditions of the infant cosmos. Its discovery by Arno Penzias and Robert Wilson in 1965 remains one of the most significant milestones in the study of the universe's origins. The CMBR not only confirms the Big Bang theory, but also continues to inform our understanding of the universe's structure and history. Its discovery was a pivotal moment, as it provided the first direct evidence that the universe had undergone an expansion from a hot, dense state. Through the study of the CMBR, scientists have gained a window into the earliest moments of the cosmos, bringing us closer to understanding how our universe began and how it continues to evolve. But it was accidentally discovered by Arno Penzias and Robert Wilson in 1965, a breakthrough that earned them the Nobel Prize in Physics. This momentous discovery, known as the cosmic microwave background radiation, CMBR, remains one of the most profound pieces of evidence supporting the Big Bang theory. It offers an invaluable glimpse into the conditions of the early universe, allowing scientists to trace the evolution of our cosmos from its infancy to its current state. The CMBR is a remarkable cosmic backdrop, almost uniform across the universe, with a temperature of approximately 2.725 Kelvin, about -274.25 degrees Celsius. This faint radiation, the afterglow of the Big Bang, is one of the most thoroughly studied phenomena in cosmology, with data collected from instruments such as the Cosmic Background Explorer (COPE) satellite, the Wilkinson Microwave Anisotropy Probe (WMAP), and more recently, the Planck satellite. These cutting-edge tools have mapped the CMBR in extraordinary detail, unveiling critical data about the universe's rate of expansion, its age, its composition, and the distribution of matter across vast cosmic distances. They have sharpened and refined our models of the cosmos, revealing new dimensions to the questions we've long asked about our universe's origins and fate. The shape and destiny of the universe are interwoven with deep cosmological questions, touching on concepts such as its geometry and its eventual evolution. These ideas rest upon crucial factors like the total mass energy content of the universe and the elusive properties of dark energy. The curvature of the universe, its overall shape, can be open, closed, or flat, each offering vastly different implications for the universe's future. A closed universe, for instance, curves back on itself like a sphere. An open universe expands outward, infinitely stretching in all directions, while a flat universe has no curvature and extends boundlessly, like an endless plane. Observations, particularly those focused on the CMBR, suggest that our universe is likely flat. This means its expansion is expected to continue indefinitely, with no end in sight. But this shape also holds the key to understanding the universe's eventual fate. If the universe remains open or flat, with insufficient mass to generate enough gravitational pull to halt its expansion, it will keep expanding forever. Over time, this would lead to a scenario known as the Big Freeze or heat death, where the universe grows colder and emptier. In this far future state, stars will burn out, black holes, neutron stars, and white dwarfs will remain, but they too will eventually dissipate, leaving behind a dark, cold, and lifeless universe. On the flip side, a closed universe could collapse upon itself in a process known as the Big Crunch. In this scenario, the universe's expansion would eventually slow, stop, and then reverse, leading to a contraction where galaxies, stars, and eventually even elementary particles would collapse back into a singularity. Some theories suggest this could result in a cyclical model of the universe, where a big crunch is followed by another big bang, restarting the cosmic cycle anew. Currently, the universe's expansion is accelerating, driven by dark energy, a mysterious and poorly understood force that works against gravity. This revelation has reshaped our understanding of the cosmos. If dark energy continues to dominate the universe's expansion, it will lead to the indefinite stretching of space, reinforcing the idea that the Big Freeze is our likely fate. The exploration of dark energy and the universe's total energy content remains one of the most exciting and profound areas of research in modern cosmology. As scientists continue to peel back the layers of the universe's most fundamental mysteries, these ideas about the cosmos's ultimate fate drive research forward, pushing the boundaries of our knowledge and our understanding of what lies ahead. Whether through the pursuit of dark energy or through deeper analysis of cosmic structure, the journey to understanding our universe's past, present, and future is a vast, evolving puzzle, one that may ultimately reveal truths that are beyond our wildest imagination. The cosmic distance ladder is an essential concept in astronomy, allowing us to measure the vast expanses of the universe in a way that is both structured and incremental. Imagine it as a series of interconnected steps, each one designed to measure distances at different scales depending on how far we need to look. For nearby stars within our own Milky Way galaxy, astronomers rely on parallax, a method that capitalizes on the apparent shift in a star's position as Earth orbits the Sun. This technique offers a direct measure of distances to stars relatively close to us. However, as we venture further out, beyond the Milky Way, the task becomes more complex. This is where standard candles such as Cepheid variable stars and Type 1a supernovae come into play. These stars are unique because their luminosity and pulsation periods are directly correlated, making them reliable markers for measuring distances. By studying their brightness, astronomers can determine how far these stars are located in space. As we move to even greater distances, Type Ia supernovae, which exhibit a consistent peak brightness, allow for precise distance measurements across cosmological scales, providing insight into the farthest reaches of the universe. Yet, for the most distant objects, we turn to redshift. Redshift measures how much the wavelength of light has stretched as the universe expands, offering vital clues about how far light has traveled. This method helps us comprehend the scale of the universe itself. The cosmic distance ladder, in essence, is a collection of tools that astronomers use to piece together the grand narrative of the cosmos, offering insight into not only how vast our universe is, but also how galaxies are distributed within the cosmic web. It even provides crucial clues about the age of the universe and its ongoing expansion. One of the greatest mysteries that still captivates cosmologists is dark energy, the enigmatic force responsible for the accelerating expansion of the universe. Despite constituting approximately 70% of the universe's total energy, the true nature of dark energy remains elusive. Initially, it was believed that the expansion of the universe would slow due to the gravitational pull of all matter. However, in the late 20th century, astronomers observed distant supernova and found that the universe was not slowing down, but expanding at an increasingly rapid pace. This observation led to the proposal of dark energy, a force that opposes gravity and accelerates the universe's growth. The implications of dark energy are profound. It has reshaped our understanding of the universe's future and even its origins. If dark energy continues to dominate, the universe may keep expanding, growing colder and emptier as time goes on, a scenario often referred to as the Big Freeze. This presents a challenge to our current understanding of physics, pushing us to develop new theories that can integrate the mysteries of dark matter, dark energy, and observable matter. By studying dark energy, we may one day unlock the fundamental laws that govern our universe, and perhaps answer one of cosmology's biggest questions: how will the universe end? Another key breakthrough in understanding the cosmos is the detection of gravitational waves, the ripples in the fabric of space-time, first predicted by Albert Einstein in his general theory of relativity over a century ago. These waves, caused by cataclysmic events such as the collision of black holes or neutron stars, carry with them crucial information about the most violent processes in the universe. Unlike electromagnetic radiation, which can be absorbed or scattered, gravitational waves travel unimpeded across the cosmos, providing astronomers with an unfiltered view of cosmic phenomena. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made its groundbreaking detection of these waves. This opened up a new avenue for studying the universe. By analyzing gravitational waves, scientists can observe events that would otherwise be invisible, such as the merger of black holes or the dynamics of the early universe, just fractions of a second after the Big Bang. As the field of gravitational wave astronomy continues to mature, it promises to unveil some of the most profound mysteries of the cosmos, including the nature of gravity itself, and offer a deeper understanding of black holes, neutron stars, and the early stages of the universe. Each of these discoveries, from the cosmic distance ladder to the detection of gravitational waves, brings us closer to unlocking the mysteries of our universe. The more we learn, the clearer it becomes that the cosmos is a vast and dynamic place, full of wonders beyond our current comprehension. As we continue to develop new techniques and technologies to explore the farthest reaches of space, we are on the precipice of answering questions that have long eluded humanity. The journey has only just begun. But it's not just about expanding our understanding of the fundamental laws that govern the universe, that it's about unveiling the hidden tapestry of existence itself. Imagine, if you will, the largest structures in the cosmos, vast cosmic webs of galaxies. These structures, known as superclusters and filaments, are so massive that their full scale defies comprehension. Stretching across hundreds of millions of light years, they form the skeleton of the universe, a colossal framework that binds together clusters of galaxies and stretches across the dark voids of space. At the heart of this grand cosmic architecture lies the Great Attractor, a mysterious gravitational anomaly in intergalactic space. This invisible force is not just a curiosity. It points to the existence of an even larger structure, the Laniakea supercluster. Encompassing our very own Milky Way galaxy and tens of thousands of other galaxies, this supercluster spans a staggering 500 million light years. It's a structure so immense that it challenges our very perception of size and scale. These superclusters and filaments are more than just collections of galaxies. They are the backbone of the universe, defining the very large-scale structure that emerged from the minute gravitational irregularities in the early universe. The discovery of these massive cosmic structures has revolutionized our understanding of the universe's evolution and composition. They serve as key evidence of the elusive forces of dark matter and dark energy, which, though invisible, are thought to be the driving forces behind the formation of these gigantic cosmic structures. By studying these gargantuan clusters and the vast voids between them, astronomers are able to trace the history of the universe itself, from the Big Bang to the present day. It's through these insights that we gain a deeper understanding of the fundamental properties that shape our cosmos, as well as the grand scale of the observable universe. Yet, there are those who wonder, is our universe the only one? This brings us to the mind-bending concept of the multiverse. The idea suggests that alongside our own universe, there could be multiple, perhaps even infinite universes, each with its own unique set of physical laws, cosmic structures, and possibly even varying constants of nature. Although this theory remains speculative and beyond our direct observation, it has its roots in some of the most groundbreaking theories in modern physics, particularly quantum mechanics and string theory. In quantum mechanics, the many worlds interpretation proposes that all possible alternate histories and futures exist simultaneously, each represented by a separate universe. It's a radical view of reality that suggests every possible outcome of every event spawns a new universe. Meanwhile, string theory, in its pursuit of reconciling gravity with quantum physics, proposes that our universe is but one of many within a vast, higher dimensional space. According to this theory, the multiverse is not just a possibility, it's an inevitable consequence of the way fundamental forces interact at the quantum level. The multiverse theory is also supported by inflationary cosmology, which posits that during the Big Bang, the universe expanded at an extraordinary rate, potentially leading to the creation of countless bubble universes, each with its own distinct set of physical properties. These bubble universes could have entirely different physical constants, laws of physics, and even realities. Though empirical evidence for the existence of other universes remains elusive, the theory provides a tantalizing glimpse into a universe that is far more complex and mysterious than we could ever have imagined. As we continue to explore the cosmos, we are left with one profound truth. The universe, in all its vastness and intricacy, holds secrets that challenge the very limits of human understanding. It offers profound implications for the way we understand the deepest questions in physics. It challenges our long-held assumptions about the uniqueness of our universe, suggesting that the cosmos we inhabit may not be the only one in existence. The multiverse concept, which pushes the boundaries of what we can observe and understand, provides a possible explanation for the fine-tuning of the cosmological constants. These constants are essential to sustaining life as we know it, and the idea that they may have been calibrated across multiple universes opens up exciting, albeit controversial, possibilities. The multiverse theory, a vast and daring framework, fits into modern physics as an expansive, yet still unproven, concept. It forces us to rethink our understanding of reality itself. How do we comprehend a universe that might not be alone, where multiple realities or dimensions exist side by side, each with its own set of physical laws? The theory challenges the very fabric of science, extending the limits of human knowledge and comprehension. It beckons us to imagine a cosmos much grander than we have ever conceived, where the boundaries between life and the laws of nature blur into something greater than the sum of its parts. But as we contemplate the ultimate fate of the universe, we must confront one of the most profound mysteries in cosmology. How will the universe end? Various theories paint different pictures of its final chapter, and each scenario depends heavily on the current state of cosmic expansion. One theory, known as the Big Freeze or heat death, suggests that the universe will continue to expand at an ever-increasing rate. As galaxies drift further apart, stars burn out, and matter becomes more diffuse, the universe will grow colder and darker, leading to a lifeless existence. This chilling vision paints a bleak picture of the universe's far future. In stark contrast, the Big Crunch presents a dramatic reversal. In this scenario, the universe's expansion halts and reverses, pulling everything back toward a central point. The force of contraction could cause temperatures and density to soar, potentially resulting in a singularity, an infinitely small, dense point from which a new universe could be born. This cyclical view of the cosmos suggests that the universe may not have a singular end, but instead undergoes eternal cycles of birth and death, stretching beyond the limits of time as we know it. Then there's the Big Rip, a violent and cataclysmic theory in which the universe's expansion accelerates exponentially, driven by mysterious forces like dark energy. In this version of the future, galaxies, stars, planets, and even atoms would be ripped apart as the fabric of space-time itself unravels. It's a scenario that seems ripped from the pages of science fiction, yet it arises from real scientific concepts that we continue to study and refine. The Big Bounce offers a cyclical model which posits that the universe undergoes a series of expansions and contractions, each Big Bang followed by a Big Crunch. This continual cycle of cosmic rebirth may represent a universe that is eternal, never truly ending, but instead cycling through infinite iterations of creation and destruction. These ideas, drawn from our present understanding of physics, cosmology, and mathematical models, highlight the speculative nature of our exploration into the cosmos. However, the future of the universe remains a mystery, and these theories are based on the current understanding of phenomena such as dark matter, dark energy, and the very fabric of space-time itself. As technology and theories evolve, we may inch closer to understanding which, if any, of these theories will ultimately shape the fate of the cosmos. One of the most intriguing frameworks in modern physics is string theory. It proposes that the fundamental particles we observe are not point-like objects, but rather tiny vibrating strings. The type of particle that emerges depends on the string's vibration. This breakthrough could unite the two pillars of modern physics: quantum mechanics, which governs the microscopic world, and general relativity, which explains the massive forces that shape the universe on a cosmic scale. String theory's promise is vast, offering a potential theory of everything, one framework that might reconcile all the forces of nature, from gravity to electromagnetism, in a single elegant model. One of the most exciting aspects of string theory is its suggestion that there could be additional dimensions beyond the familiar four of space and time. In fact, string theory predicts up to 6 or 7 hidden dimensions that are compactified and exist at scales far too small for us to observe directly. These extra dimensions could offer insights into the nature of the universe and its fundamental forces. While string theory lacks direct experimental evidence and poses significant challenges to testing its predictions, it has generated immense interest in the scientific community. It could hold the key to unlocking some of the most pressing questions in physics, such as the true nature of black holes or the unification of the fundamental forces. In parallel with string theory, quantum mechanics has already revolutionized our understanding of the subatomic world. Principles like wave-particle duality, quantum entanglement, and superposition suggest that particles can exist in multiple states at once until measured. This defies classical notions of reality and challenges our perceptions of space and time. As we venture deeper into quantum mechanics, it holds the potential to reshape our view of the universe in profound and unexpected ways. One of the most exciting frontiers in quantum mechanics is quantum gravity, which seeks to merge quantum mechanics with general relativity into a single cohesive theory. This could provide new insights into the mysteries of dark matter, dark energy, and the very fabric of space-time itself. Quantum computing, another area of immense potential, leverages the strange properties of quantum mechanics to perform calculations far beyond the reach of traditional computers. This could revolutionize fields ranging from material science to cosmology, enabling us to simulate entire universes or unlock new approaches to solving complex problems in medicine and technology. As we continue to explore the quantum realm, we are confronted with profound philosophical questions about the nature of reality, the limits of human knowledge, and our understanding of determinism and causality. Ultimately, as our understanding of quantum mechanics and other theoretical frameworks deepens, we may find ourselves on the verge of unveiling new technologies and insights that could transform our world. The future of physics holds incredible promise, and as we push the boundaries of knowledge, we may uncover secrets of the universe that have long eluded us. The journey is just beginning, and the possibilities are endless. But also to offer profound insights into the workings of the universe at its most fundamental level, uniting quantum mechanics and general relativity into a single all-encompassing theory is considered one of the greatest challenges in modern physics. This monumental task demands the reconciliation of two seemingly incompatible frameworks, one governing the infinitesimally small, and the other, the vast expanse of cosmic phenomena. The primary difficulty arises from the fundamental differences in how these two theories describe the universe, creating a chasm between them that has yet to be crossed. Quantum mechanics operates in the realm of the very small, delving into particles and forces at the atomic and subatomic levels. Here, the universe is governed by probabilities, with outcomes described in terms of likelihoods rather than certainties. It's a world of uncertainty where the very act of measurement can alter the outcome, and where particles can exist in multiple states simultaneously, all until they are observed. In stark contrast, general relativity deals with the large-scale structure of the universe, describing gravity as the curvature of space-time caused by the presence of mass and energy. It's a smooth, continuous model where massive objects like stars, planets, and galaxies warp the fabric of space-time, creating what we perceive as gravity. The fundamental issue lies in their inherent contradictions. Quantum mechanics suggests a discrete, quantum nature of phenomena, while general relativity treats space-time as a smooth continuum. This discrepancy creates a conceptual challenge when trying to imagine a quantum theory of gravity, where space-time itself would be quantized, possibly composed of tiny, indivisible units. This quantum structure would mean that at the smallest scales, space-time behaves differently, potentially exhibiting properties that challenge our classical understanding of the universe. Moreover, general relativity, as a classical theory, does not incorporate the principles of uncertainty and superposition, which are fundamental to quantum mechanics. These two worlds exist in separate realms, their principles not easily aligned. When we attempt to apply quantum rules to the gravitational field, we encounter mathematical inconsistencies, like infinities, that cannot be simply erased or ignored. This mismatch between theory and reality is one of the most profound obstacles in modern physics. Despite this, both quantum mechanics and general relativity have been tested and validated with astonishing precision within their respective domains. Yet, the pursuit of a unified theory, often referred to as quantum gravity, remains elusive. The experimental challenges in testing theories like string theory and loop quantum gravity are enormous. The scales at which these effects manifest are so small, and the energies required to probe them so high, that current technology cannot measure or observe them directly. But the effort continues, for bridging the gap between these two theories promises not only to reveal the deepest secrets of the universe, but also to redefine the very fabric of reality itself. As we look forward, the future of space travel is poised for a revolution, fueled by emerging technologies that have the potential to break through the existing limitations of cost, speed, and efficiency. One of the most anticipated advancements is nuclear propulsion, which could drastically reduce travel times within our solar system. Unlike traditional chemical rockets, nuclear propulsion systems such as nuclear thermal or nuclear electric propulsion offer much higher efficiency and thrust. In practical terms, this could cut the journey to Mars by half, transforming our ability to explore the planets and beyond. Another groundbreaking innovation is the development of reusable rockets, a concept pioneered by companies like SpaceX. This technology has the potential to dramatically reduce the cost of accessing space. By enabling spacecraft to be launched, landed, and reused multiple times, space travel becomes not only more efficient, but economically viable. This breakthrough has the power to unlock the door to a future where space exploration is no longer reserved for government agencies alone, but open to private enterprise and broader participation. Then there's the concept of space elevators, towers that stretch from the Earth's surface into space, providing a continuous, energy-efficient means of transport. Although still constrained by the limits of current material science, space elevators could provide an entirely new way to access the cosmos. If realized, they would bypass the need for expensive rocket launches, allowing for the transport of materials and people into orbit with far less cost. Looking even further into the future, advanced materials and manufacturing techniques, including 3D printing in space, hold the promise of transforming how we build spacecraft and even habitats. The ability to construct structures directly in orbit or on celestial bodies would drastically reduce the need to launch materials from Earth, making long-duration space missions and colonization much more feasible. The possibilities for humanity's future in space are expanding, and with each technological breakthrough, we move one step closer to making the dream of living among the stars a reality. Quantum communication technology has emerged as a groundbreaking innovation that promises to revolutionize secure communication across the vast stretches of space. This technology is expected to support more advanced exploration missions and may even pave the way for human habitation on other planets. As this and other emerging technologies continue to evolve, they hold the potential to not only extend our reach within the solar system, but also radically transform our understanding of space travel and the possibilities of life beyond Earth. What was once the realm of science fiction is now inching closer to reality, bringing the cosmos within reach like never before. One of the most intriguing concepts to come out of theoretical physics is the idea of wormholes. These theoretical passages through space-time are often imagined as shortcuts, connecting two distant points in the universe. In essence, a wormhole could act as a bridge across the cosmos, making interstellar travel feasible within a fraction of the time it would take using conventional means. Such a mechanism could also open the door to travel between different dimensions or even parallel universes. The concept of wormholes arises from solutions to the equations derived from Albert Einstein's general theory of relativity, although they remain hypothetical and have never been observed. Despite their theoretical nature, wormholes continue to captivate scientists and remain a subject of intense research and speculation. Under certain conditions, these wormholes could even enable time travel. The key idea lies in the concept of time dilation, a relativistic effect where time moves slower for an object traveling at near light speeds compared to a stationary observer. If one end of a wormhole were to remain stationary while the other end traveled at a significant fraction of the speed of light, time could flow differently at each end of the tunnel. This differential could, in theory, enable time travel, allowing one to traverse the fabric of time itself. However, while the theory sounds compelling, there are immense challenges to overcome. For one, existing theories suggest that any wormhole would collapse quickly without a stabilizing force, something that theoretical physicists call exotic matter, which could potentially possess negative energy density and negative pressure. This exotic matter has yet to be discovered in the form necessary to keep a wormhole open long enough for meaningful travel. Furthermore, while general relativity supports the concept of wormholes, quantum mechanics introduces further complexities, complicating our understanding of how these phenomena might work in practice. To fully grasp the potential and limitations of wormholes and time travel, a unified theory of quantum gravity, which combines general relativity and quantum mechanics, would be essential, a goal that remains elusive in modern physics. As tantalizing as the possibility of time travel and interstellar wormhole travel may be, it is important to note that practical applications, including the use of wormholes for time travel, remain speculative and far beyond our technological capabilities. Nevertheless, the notion of wormholes continues to inspire physicists and space enthusiasts alike, as it pushes the boundaries of what we know and challenges our fundamental understanding of space-time. At the same time, humanity is increasingly focusing on the dream of colonizing other planets, propelled by technological advancements and a growing understanding of the solar system. While the idea of establishing human colonies beyond Earth comes with monumental challenges, it is becoming ever more feasible, especially with efforts directed toward our nearest neighbors, Mars and the Moon. Colonization of these celestial bodies will require overcoming a series of unprecedented obstacles, such as providing sustainable life support systems, protecting inhabitants from cosmic radiation, and addressing the psychological toll of long-term isolation. Additionally, the creation and transportation of infrastructure, supplies, and resources necessary to support human life on planets with vastly different environments will require breakthroughs in technology and engineering. On Mars, for example, the challenges are immense. Scientists must find ways to produce oxygen, water, and food locally, as well as shield colonists from harmful radiation. Propulsion systems capable of sending humans to Mars and back will also need further development. However, technological innovations are already underway in key areas like closed-loop life support systems, habitat construction, and space farming, which could significantly enhance the feasibility of planetary colonization. In situ resource utilization, ISRU is particularly crucial for reducing costs and logistics. By utilizing local resources, such as extracting water ice from Martian soil, or using local materials for building habitats, humanity can reduce its reliance on Earth for critical supplies. These developments are not just theoretical, they are rapidly being tested and refined in a variety of space missions. The collaboration between government space agencies such as NASA, the European Space Agency, ESA, and Roscosmos, as well as private companies like SpaceX and Blue Origin, has accelerated the pace of space exploration. With these combined efforts, space colonization is becoming less of a distant dream and more of an achievable goal for the near future. As we move closer to a reality where humanity is capable of traveling across the stars and potentially establishing a presence on other planets, quantum communication, wormholes, and other advanced technologies will play pivotal roles in shaping our future in space. Though many challenges remain, the technological landscape is changing rapidly, and each breakthrough brings us one step closer to becoming an interplanetary species. The cosmos is no longer just a distant frontier. It's a destination we are learning to reach. In the ever-evolving world of space exploration, SpaceX's development of the Starship spacecraft stands as a monumental leap toward transforming the dream of making human life multiplanetary into a tangible reality. This ambitious project is focused on Mars, aiming to establish the first human colonies beyond Earth, and ultimately set the stage for human settlement on other planets. But even though the goal is clear, the journey ahead is anything but simple. Colonizing other planets presents a complex array of challenges, from technological and environmental hurdles to social and ethical dilemmas. But there's hope. Ongoing advancements in space technology, combined with growing international interest in space exploration, are rapidly improving the prospects of establishing permanent human settlements beyond Earth. What once seemed like science fiction is gradually becoming within our reach. The technological breakthroughs we're witnessing are not just limited to building faster spacecraft or more efficient propulsion systems. They also include critical developments in human physiology and psychology that will help us address the challenges of living and thriving in the harsh environments of other worlds. Yet, these breakthroughs are only the tip of the iceberg. To overcome the barriers to becoming a multiplanetary species, we must ensure that these advancements are combined in a way that can support sustainable life on distant planets for generations. However, this journey to other worlds is not without its ethical challenges. As humanity expands its reach into the cosmos, we must grapple with a host of complex ethical considerations spanning environmental, social, and philosophical domains. The responsible stewardship of outer space becomes imperative as we seek to explore, utilize, and protect these new frontiers. One of the most pressing ethical concerns involves the potential contamination of celestial bodies, a process that could disrupt the pristine conditions of these distant worlds. This issue, known as planetary protection, raises the specter of two primary risks: forward contamination, the unintended transport of Earth-based microbes to other planets, and backward contamination, the risk of bringing extraterrestrial organisms back to Earth. Preserving the integrity of other worlds is crucial, not just for the sake of scientific research, such as the search for extraterrestrial life, but also out of respect for the inherent value of these environments. After all, we are tasked with protecting the wonders of the universe for future generations of explorers, while ensuring that we don't unknowingly alter the natural state of these worlds. Moreover, as our capabilities expand, so too the ethical questions surrounding the utilization of space resources. Mining asteroids, extracting water from the moon, or harvesting other resources in space introduces concerns about ownership, exploitation, and the equitable distribution of these space-derived benefits. These issues go beyond corporate interests and touch on deeper questions about the common good and the role of spacefaring nations in the governance of the cosmos. This is where the Outer Space Treaty of 1967 becomes essential, as it recognizes space as the province of all mankind and underscores the need for space activities to benefit humanity as a whole, not just a select few. But ethical dilemmas don't end there. The accumulation of space debris has become an increasingly dire problem. As satellites, spacecraft, and space stations continue to fill Earth's orbit, the risk posed by this debris grows. Collisions with space debris could potentially endanger current and future space missions, threatening the viability of long-term space exploration. This escalating issue calls for more sustainable practices in space operations and a coordinated global effort in debris mitigation to ensure that we don't inadvertently close the door on our future in space. Colonizing other planets brings its own set of ethical considerations, raising questions about the potential displacement of extraterrestrial life, should we find it, and the governance of space colonies. Who will govern these new frontiers? What measures will be put in place to preserve Earth's diversity and cultures in extraterrestrial colonies? These challenges will require careful thought and collaborative efforts from scientists, policymakers, and ethicists to ensure that our exploration of the unknown is guided by principles that promote both responsibility and respect for all life forms. As we step further into the vastness of space, it's clear that our exploration efforts must be underpinned by ethics and open dialogue. Science, ethics, and policy must intersect in thoughtful ways to navigate this uncharted territory. Only then can we ensure that our venture into the cosmos is done with foresight, respect, and responsibility, protecting not only our home planet, but also the vast and untapped potential of the universe at large. Meanwhile, simulations serve as an invaluable tool in understanding the complexities of the cosmos. By inputting physics equations and initial conditions into powerful computers, scientists can generate simulations that mirror the vast phenomena of the universe. These simulations allow us to test hypotheses and explore cosmic phenomena in ways that would otherwise be impossible. From the formation of galaxies to the dynamics of black holes, simulations serve as a bridge between theoretical models and real-world observations, providing key insights into the workings of the universe. But these digital models are more than just abstract exercises in theory. They offer practical benefits, helping scientists refine their understanding of everything from gravitational forces to the behavior of space-time itself. By testing out these theories in simulations, we are unlocking the mysteries of the cosmos, and with each new discovery, we edge closer to unraveling the truths of existence easier, while ensuring that our place in the universe is not just observed, but respected and understood. Space exploration is not just about reaching new worlds. It's about expanding the boundaries of human potential while keeping our feet grounded in ethical responsibility. The universe is vast, and it's up to us to explore it with respect, diligence, and an unwavering commitment to the greater good. Cosmological simulations are an extraordinary tool in modern science, enabling researchers to track the evolution of the universe from its inception shortly after the Big Bang to the present day. These simulations provide us with invaluable insights into the enigmatic forces that shape our cosmos, such as dark matter and dark energy, crucial components of cosmic structure formation. By simulating the behavior of billions of galaxies, dark matter, and other cosmic phenomena, scientists can uncover patterns and outcomes that are often not immediately apparent from theoretical equations alone. Through these simulations, we gain access to a level of complexity that allows us to visualize the universe's workings in ways once thought impossible. What's even more remarkable is the ability of these simulations to explore scenarios that cannot be studied directly. Many cosmic events, especially those spanning millions or even billions of years, remain out of reach for traditional observation due to limitations in technology or the sheer distances involved. Yet, by adjusting the parameters and initial conditions in a controlled digital environment, scientists can model a vast array of possibilities, helping refine our understanding of physical laws and predict the outcomes of phenomena that have yet to be observed. These simulations also play a crucial role in guiding both observational campaigns and experiments. For example, by simulating gravitational wave signals from merging black holes, researchers can better identify these waves in real data, enhancing the likelihood of making groundbreaking discoveries in the field of astrophysics. Simulations not only extend our reach into the most distant corners of the universe, but they also help improve the precision of the tools we already have. As a result, they serve as an indispensable part of the modern scientific toolkit, one that helps guide new explorations into cosmology, astrophysics, and beyond. They enable a deeper, more nuanced understanding of the universe, offering us a clearer picture of its myriad mysteries. In the face of such vast and complex phenomena, simulations become the bridge between theory and reality, allowing us to test hypotheses and push the boundaries of human knowledge. The role of artificial intelligence in space exploration. Artificial intelligence, AI, is poised to revolutionize space exploration, opening up new frontiers in data analysis, decision-making, and automation. As space missions grow more ambitious, AI's potential to transform these missions cannot be overstated. From mission design and planning to daily operations and real-time data interpretation, AI could provide the critical edge that future space explorers will need. One of the most significant applications of AI lies in its ability to manage the vast amounts of data generated by space telescopes and planetary missions. Machine learning algorithms can sift through this data much faster than human scientists, identifying patterns, classifying celestial objects, and detecting phenomena that might otherwise go unnoticed. In turn, this accelerated data processing could lead to major breakthroughs in the search for exoplanets, understanding galaxy formation, and even identifying signs of extraterrestrial life. Another pivotal role of AI could be in the realm of mission autonomy. As spacecraft and rovers venture further from Earth, communication delays caused by the vast distances between planets can pose significant challenges. AI can enable these missions to make real-time decisions on the spot without having to wait for instructions from Earth, which may take minutes or even hours to arrive. This capability is especially vital for conducting research in remote or harsh environments like the surface of Mars or the icy moons of Jupiter. In these extreme conditions, immediate responsiveness can greatly enhance mission safety, productivity, and the ability to explore regions of the solar system that would otherwise be difficult or impossible to study. AI's potential in space exploration extends to the construction of habitats and infrastructure on other planets. AI-driven robots could take on tasks that are far too dangerous or impractical for humans, such as mining resources, building shelters, or setting up solar arrays. These robots could lay the groundwork for human colonization of distant worlds, ensuring that astronauts will have the necessary resources and habitats to survive. Moreover, AI could also play a vital role in monitoring astronaut health, tracking vital signs, and offering real-time medical advice during long-duration missions. As we look toward the future of space exploration, particularly with ambitious goals like establishing a sustainable human presence on the Moon or Mars, AI will become an integral part of making these dreams a reality. Particle physics discovering the unknown. The frontier of particle physics, where scientists seek to uncover the fundamental particles that make up our universe, is one of the most exhilarating and dynamic areas of modern science. As technology advances, we stand on the precipice of making unprecedented discoveries about the very building blocks of matter. The Large Hadron Collider, LHC, the world's most powerful particle accelerator, operates at energies of up to 13 trillion electron volts, offering researchers a glimpse into the heart of subatomic particles that have long eluded detection. In 2012, the discovery of the Higgs boson, once thought to be purely theoretical, confirmed the existence of this crucial particle, showcasing the immense potential for new discoveries within the realm of particle physics. Physicists are now turning their attention to particles beyond the Higgs boson, such as supersymmetric particles, which could hold the key to solving long-standing mysteries like dark matter. The theoretical framework suggests that the universe is filled with particles that have yet to be detected, each one representing a missing puzzle piece that could dramatically change our understanding of physics. As we continue to explore this invisible world of particles, the promise of new discoveries remains ever present. Each potential new particle could redefine the way we think about the universe, challenging our deepest assumptions about the nature of reality itself. The search for habitable worlds, the Goldilocks zone. In the ongoing quest to find planets that could support life, astronomers use a set of criteria that serve as their guiding compass, much like navigators charting their course by the stars. At the heart of this search is a concept known as the Goldilocks zone. This is the region around a star where the conditions are just right for liquid water to exist, neither too hot nor too cold, making it a potential home for life as we know it. Along with the planet's position within this habitable zone, other factors come into play, such as the planet's size and mass. A planet must be large enough to retain an atmosphere, but not so large that it becomes a gas giant. The presence of an atmosphere is also crucial, as it offers protection from harmful radiation while potentially containing the chemical ingredients necessary for life. These criteria help astronomers narrow down the vast number of planets in the universe, focusing their efforts on those that share similarities with Earth. But the search for exoplanets, the planets that orbit stars outside our solar system, is far from simple. To detect these distant worlds, astronomers employ an array of fascinating techniques, with one of the most productive being the transit method. This technique monitors the light from a star and looks for the slight dimming that occurs when a planet passes in front of it. This brief but significant dip in brightness not only indicates the presence of a planet, but can also provide valuable information about its size, orbit, and potential for habitability. As astronomers continue their search, each discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? But also, it is through the ingenuity of groundbreaking techniques, such as radial velocity, that we have made significant strides in unraveling the mysteries of our universe. This method, which detects the subtle wobble of a star caused by the gravitational tug of orbiting planets, reveals more than just the existence of these distant worlds. The wobble alters the star's light, stretching and compressing its wavelengths, providing astronomers with critical data about a planet's mass, orbit, and other characteristics. These techniques have revolutionized our understanding, transforming exoplanets from mere theoretical concepts into an established area of intense scientific inquiry. As these revelations unfold, we are discovering not just new planets, but diverse and complex worlds, many of which exist in the habitable zones of their stars. The painstaking efforts of astronomers, combined with the precision of modern instruments, have slowly begun to unveil the secrets of the cosmos, one exoplanet at a time. This deepening understanding has sparked further interest in the possibility of life beyond Earth, directing our attention to not only distant stars, but also to places within our own solar system. Mars, once thought to be barren and lifeless, now offers compelling evidence of a potentially habitable past. Ancient riverbeds, vast deserts, and frozen reservoirs of water ice suggest that Mars might have once hosted life, or could still harbor life in protected niches beneath its surface. The search doesn't stop there, however. The icy moons of Jupiter and Saturn, Europa, Enceladus, and Titan, are equally intriguing. Beneath their frozen exteriors, subsurface oceans exist, environments that might shield potential life from the harshness of outer space. Europa, in particular, with its potential for hydrothermal activity, stands out as a prime candidate in the quest to discover habitable zones beyond Earth. But the exploration doesn't end with our solar system. We now turn our gaze to exoplanets that lie within the habitable zones of their stars, regions where conditions might be right for liquid water, a critical ingredient for life. Planets like Proxima b, orbiting our closest stellar neighbor, Proxima Centauri, hold the promise of water on their surfaces and, perhaps, life. These exoplanets represent the cutting edge of our search for life beyond Earth, guiding our explorations and offering tantalizing possibilities. Their unique environments expand the horizons of our search, fundamentally reshaping our understanding of life in the universe. Proof of life beyond Earth, however, would not come easily. The evidence must be incontrovertible, withstanding the rigorous scrutiny of the scientific community. The discovery of microbial fossils embedded in rock formations on Mars, similar to early life forms on Earth, would provide solid, tangible proof. Similarly, evidence from the icy moons of Jupiter and Saturn might come from the analysis of plumes of water shot into space, revealing organic compounds or microbial life thriving in their subsurface oceans. On exoplanets, the search would be more nuanced, focusing on the chemical composition of their atmospheres. The detection of biosignature gases, such as oxygen, ozone, methane, and carbon dioxide, could hint at biological processes occurring on these distant worlds. The search for extraterrestrial life could also reveal a chemical imbalance in a planet's atmosphere, a phenomenon that would be best explained by the presence of living organisms. Such a discovery, while indirect, could serve as a strong signal that life exists elsewhere. Ultimately, confirming the existence of extraterrestrial life may require a combination of evidence: direct signs such as microbial life or biochemical signatures, along with indirect markers like atmospheric biosignatures or changes to a planet's surface. This multi-pronged approach would offer compelling evidence that we are not alone in the universe, a discovery that could reshape our understanding of life itself. The search for life beyond Earth is not just a scientific endeavor. It is a journey that captivates the human imagination and stirs deep philosophical and ethical questions. It forces us to confront fundamental issues of consciousness, intelligence, and the potential for communication with non-human entities. Beyond the realm of science, this quest spills over into culture, theology, and ethics, prompting discussions about the very nature of existence. As we probe deeper into the universe, the technology and knowledge we develop have tangible benefits here on Earth, advancing fields as varied as astrobiology, chemistry, and environmental science. These insights not only expand our understanding of the cosmos, but also demonstrate the interconnectedness of life on Earth with the broader universe. The more we learn about the universe, the more we realize just how much there is yet to discover, each step bringing us closer to understanding our place in the vastness of space. Moreover, the search for life beyond Earth is far more than just a scientific mission. It has evolved into a unifying endeavor that transcends national, cultural, and ideological boundaries. It brings humanity together in a shared quest to explore the universe, reminding us of our common heritage and destiny. As we extend our reach into the stars, this pursuit fosters a collective sense of responsibility for our home planet, urging us to protect Earth even as we strive to discover new worlds. The possibility of finding extraterrestrial life has the potential to revolutionize every facet of our understanding of biology, society, technology, and even philosophy. For some, the search for life beyond Earth is not merely a scientific endeavor. It is an expression of humanity's boundless curiosity and our unrelenting drive to explore the unknown. This quest reflects the deepest corners of our collective soul, shedding light on both our hopes and our fears, and opening up new possibilities for the future. When we think of extraterrestrial life, it's not just about finding another species. It's about discovering that the universe holds more mystery, more life, and more potential than we ever imagined. If we were to find even microbial life on another planet or moon, it would be a profound moment in human history, reshaping our understanding of what life is and where it can exist. Such a discovery would challenge the very essence of biology and chemistry, forcing us to confront a fundamental question: is Earth the only cradle of life in the universe, or is it just one of many? This realization would significantly increase the likelihood that life exists in various forms across the cosmos. It would mark a new chapter in the field of astrobiology, where scientists would gain their first real-world subjects beyond our planet. This breakthrough would fuel further exploration as we look not only for microbial life, but also for more complex life forms, potentially guiding humanity in its search for life on other planets. The discovery of extraterrestrial microbial life would lead to an urgent re-examination of life's origins on Earth. Are we all part of the same cosmic family, sharing a common ancestry, or did life emerge independently in different places? This would open up new frontiers in science as we begin to explore the possibility of a universal recipe for life, a set of conditions that allows life to emerge wherever the right ingredients exist. Understanding how life adapts to vastly different environments would deepen our comprehension of life's resilience and flexibility, showing just how extraordinary and adaptable it can be. The social implications of such a discovery would be equally profound. Knowing that we are not alone in the universe would undoubtedly shift the way we view ourselves. Philosophical, theological, and existential frameworks that have been in place for millennia would be forced to adapt. How could they not? The realization that life can exist in forms vastly different from our own challenges us to reconsider our place in the cosmos, forcing us to rethink what makes Earth and humanity so unique. A discovery like this wouldn't just influence our worldview. It would have practical implications for future space exploration. For instance, it would likely affect how we plan missions to distant planets and moons. With the discovery of life beyond Earth, the concept of biological contamination between worlds would take on new urgency, requiring rigorous ethical standards to prevent harm to extraterrestrial ecosystems. This would also raise new questions about the ethics of exploration. Should we as a species have the right to interfere with these life forms, or is our responsibility to preserve and protect them? The discovery of microbial life would likely spark debates about the ethics of human expansion into space and the preservation of life in all its forms. However, the stakes rise significantly if we were to discover intelligent extraterrestrial life. This would undoubtedly be one of the most earth-shattering revelations in human history. Imagine the vast array of emotions that would sweep across the globe: awe, wonder, curiosity, fear, and everything in between. For some, the very thought that we are not alone in the universe would be an overwhelming source of joy and amazement. For others, the discovery would be unsettling, even terrifying, as they ponder the potential implications. What is the nature of these beings? Are they friendly? Do they pose a threat to humanity? While the initial reaction may be one of awe, the practical realities would quickly set in. We would be driven by an insatiable need to learn more. How do these beings communicate? What technologies do they possess? What kind of societies have they built? These questions would fuel a new age of scientific inquiry as we work to understand the civilization that lies beyond our own. Governments and organizations worldwide would likely come together in unprecedented ways, forging international collaborations aimed at making contact, understanding, and learning from these extraterrestrial intelligences. Diplomatically, this discovery would be fraught with complexities. The idea of interstellar diplomacy would become an urgent matter of concern. How do we establish communication with an entirely different species? What guidelines should govern our interactions with non-human intelligences, especially if they possess technologies far beyond our own? These are questions that humanity would have to answer, forging a new path in the history of human exploration. Ultimately, the discovery of intelligent extraterrestrial life would mark a monumental turning point in human history. It would force us to expand our perspectives, question our place in the universe, and redefine what it means to be human. It would not just spark scientific curiosity, but ignite a global conversation about who we are and what lies beyond the stars. As we prepare for this possibility, one thing is certain: the universe will never seem the same again. But a profound cultural and psychological shift is inevitable as humanity faces the reality of other intelligent beings in the universe. The implications of discovering extraterrestrial life are not just scientific, they are deeply philosophical, shaking the very foundations of our beliefs, perceptions, and understanding of existence. As we confront this new reality, we will be forced to reevaluate some of humanity's most sacred assumptions. Firstly, the discovery of intelligent extraterrestrial life challenges the anthropocentric view that has long positioned humanity as the most significant or central entity in the universe. For centuries, our species has viewed itself as the pinnacle of existence, the crown of creation. The recognition that other intelligent beings could inhabit the cosmos would upend this belief, forcing us to reconsider our place in the universe. We would have to acknowledge that we are not the sole architects of intelligence, nor the only witnesses to consciousness in this vast and awe-inspiring cosmos. This newfound awareness would invite us to see humanity as just one thread in an expansive tapestry of life, where we are no longer exceptional but part of a much larger, interconnected whole. This shift wouldn't stop at questioning human exceptionalism. It would reignite ancient philosophical debates about the nature of consciousness, intelligence, and the possibility of cross-species communication on a cosmic scale. Are human ways of thinking, reasoning, and perceiving the world entirely unique to us? Or do they share common ground with other intelligent life forms? Could we bridge the divide between species, finding new ways to communicate, understand, and collaborate with entities whose minds and perspectives are vastly different from our own? Such a discovery would force us to confront the limits of our current understanding of cognition and perception, opening up new realms of inquiry and exploration. Ethical considerations would take center stage, demanding that we reevaluate our responsibilities, not just toward fellow humans, but toward all sentient beings, regardless of their origin. If intelligent extraterrestrial life exists, what duties do we have toward them? How do we balance our own survival with the rights and well-being of these unknown beings? The very framework of ethical theory could undergo a radical transformation, expanding to encompass not only all humans and terrestrial life forms, but every sentient entity across the universe. This universalist approach might reshape how we treat life on Earth as well, prompting a shift in how we engage with our environment, fellow creatures, and potentially extraterrestrial life. The recognition of intrinsic value in all sentient beings could encourage a new ethic of respect, empathy, and responsibility, a cosmic moral framework grounded in consciousness wherever it may be found. Moreover, The discovery of extraterrestrial life would inevitably challenge theological doctrines, many of which have been centered around human beings and our unique place in creation. Such a revelation would spark intense theological debate as religious communities grapple with how the existence of other life forms fits into their understanding of God, creation, and the universe. Would these beings share in the divine image? Could they possess spiritual consciousness? How might this discovery reshape religious narratives and spiritual beliefs that have long defined humanity's relationship with the cosmos? The implications would reach far beyond the realms of science and philosophy, prompting dialogues within and across faiths about the place of extraterrestrial life in the divine plan. In short, the discovery of extraterrestrial life would not merely be a scientific breakthrough. It would serve as a philosophical catalyst, prompting a sweeping re-examination of humanity's understanding of life, intelligence, morality, and our place within the universe. It would invite us to expand our horizons, urging us to adopt a more cosmic perspective on existence. This shift could be transformative, pushing us to reconsider everything from our most deeply held beliefs to our sense of responsibility on a universal scale. Across the globe, different cultures have long imagined encounters with extraterrestrial beings, shaping these visions through the lens of their own unique histories, philosophies, and spiritualities. From films and television to literature and journalism, media outlets worldwide offer a fascinating look at how societies conceive of and relate to the possibility of alien life. Western depictions often oscillate between two extremes: benevolent, wise visitors offering knowledge and aid to humanity, or hostile invaders bent on destruction. These narratives reflect a mix of hope, fear, and curiosity, mirroring humanity's age-old fascination with the unknown. Classic films like E.T. the Extraterrestrial and Close Encounters of the Third Kind showcase the potential for peaceful interaction, while War of the Worlds and Independence Day tap into our primal fears of invasion and survival. In contrast, Asian media, rich in cultural and philosophical diversity, often blends science fiction with deeper spiritual and philosophical themes. Japanese anime and manga, for example, frequently incorporate ancient myths and cosmic visions, blending futuristic technologies with a reverence for the natural world. Here, extraterrestrial beings are not just alien invaders, but are woven into the fabric of a greater cosmic order, often embodying wisdom, harmony, and interconnectedness. Indigenous and Aboriginal cultures, too, have long woven stories of star beings and celestial encounters into their cultural traditions. These narratives often reflect a profound understanding of the universe as a living, interconnected whole, where encounters with beings from the stars are seen as part of an eternal cycle of existence that transcends earthly boundaries. The rich diversity of these cultural perspectives invites a broader understanding of what extraterrestrial life could mean for humanity. It challenges us to imagine not just what these beings could look like or how they might behave, but how they could challenge and enrich our very understanding of life, intelligence, and the universe. These diverse imaginings remind us that the discovery of extraterrestrial life would be more than just an encounter with beings from another world. It would be a profound invitation to rethink everything we thought we knew about ourselves, our place in the cosmos, and the very nature of existence. In recent years, the portrayal of extraterrestrial life in various forms of media has evolved into a complex and multifaceted reflection of humanity's deep curiosity about the cosmos. These representations often serve as a mirror, revealing not just our fascination with the unknown, but also our profound fears, hopes, and existential questions about our place in the universe. From sci-fi blockbusters to thought-provoking documentaries, the depiction of alien life reflects a rich mosaic of human imagination, exploring both the potential for connection and the lurking dread of the unknown. As we look to the skies, we can't help but wonder, are we truly alone, or is someone or something watching us from the vast expanse of space? In this landscape of discovery and intrigue, private companies are becoming key players in the search for extraterrestrial life, expanding the efforts traditionally led by government space agencies. This marks a groundbreaking shift in how space exploration is carried out, blending innovation with collaboration and opening up space to new participants. These private entities, once on the fringes of space exploration, are now at the forefront, bringing fresh perspectives and technological advancements that are accelerating humanity's quest to understand what lies beyond Earth. One of the most significant contributions from private companies comes in the form of cutting-edge technologies. Take, for example, the highly sophisticated telescopes capable of detecting distant exoplanets and analyzing their atmospheres for signs of life. These tools, developed by companies such as SpaceX and Blue Origin, are revolutionizing the way we explore the cosmos, pushing the boundaries of what is possible. From launching advanced rovers to Mars to creating spacecraft that can venture into deep space, private companies are helping to expand our reach beyond our home planet, exploring celestial bodies that could harbor signs of life, past or present. SpaceX in particular has made waves by drastically reducing the cost of space travel, making it not only more accessible, but also enabling a greater number of astrobiology missions. Their work with launching satellites and interplanetary spacecraft has opened up new avenues for understanding the environments of distant planets and moons, places where life may have once thrived or could still exist today. The innovation and competition driven by these companies are accelerating progress, leading to breakthroughs in technology that could unlock the mysteries of extraterrestrial life. However, private companies aren't working in isolation. They are part of a larger ecosystem of collaboration that involves international space agencies and research institutions. Together, these entities are forming a united front in the search for life beyond Earth. The competition among private companies, fueled by the desire to outpace one another, is accelerating technological advancements and increasing the speed at which new missions are launched. This competitive spirit is not only driving progress, but is also making space exploration more cost-effective and efficient. Despite the tremendous strides made by private industry, the challenges of exploring space remain formidable. The vast distances that separate us from the stars present a technological hurdle that remains largely unsolved. Even the nearest stars are light years away, requiring propulsion technologies that are far beyond our current capabilities. The harsh conditions of space, extreme temperatures, radiation, and the vacuum of space demand advanced life support systems that can protect astronauts on long-duration missions. These technological barriers continue to constrain our ability to send humans to distant worlds. Physiologically, the human body faces numerous challenges in space. Microgravity, for example, leads to muscle atrophy and bone density loss, while exposure to cosmic radiation increases the risk of cancer and other health issues. These challenges significantly limit the duration of space missions, making it difficult to envision long-term human settlements on distant planets like Mars. Without significant advancements in countermeasures, these health risks will remain a major roadblock in the quest to establish a permanent human presence beyond Earth. Economically, the costs of space exploration remain staggering. The financial investment required to develop, launch, and maintain missions is immense, and space agencies and private companies alike must balance scientific ambitions with the realities of limited resources. Despite the involvement of private companies, which have introduced new funding and technological innovations, the financial demands of overcoming technological and physiological obstacles continue to present significant challenges. Yet, despite these obstacles, the drive to explore the cosmos remains unshaken. Human ingenuity, combined with international cooperation and the increasing involvement of the private sector, is steadily pushing the boundaries of space exploration. Advancements in spacecraft design, propulsion systems, and life support technologies are helping to overcome many of these challenges. Furthermore, public-private partnerships are fostering innovation that could pave the way for more ambitious missions and a deeper understanding of our universe. In this new era of space exploration, private companies are not just participating, they are actively shaping the future of how we explore and understand life beyond Earth. The collaboration between public agencies and private industry is accelerating progress, making what once seemed like science fiction a very real possibility. As spacecraft design continues to evolve, material science, computational technology, and engineering breakthroughs are pushing humanity closer to answering one of the most profound questions of all. Are we alone in the universe? The journey ahead is long and fraught with challenges, but humanity's drive to reach the stars is unwavering. Whether through private or public efforts, the search for extraterrestrial life is a testament to our collective curiosity and unyielding quest for discovery. As the boundaries of space exploration expand, we stand at the cusp of a new age, one where the cosmos may no longer be an unreachable mystery, but a destination within our grasp. Space exploration is undergoing a remarkable transformation, driven by cutting-edge technological advancements and a new era of collaboration between public agencies, private companies, and international partnerships. As we venture further into the cosmos, the very nature of spacecraft design is being redefined, paving the way for a future where human presence in space and exploration of distant planets is not just a dream, but a tangible reality. One of the most transformative developments in recent years is the increasing use of reusable spacecraft, with SpaceX's Falcon rockets and Dragon capsules leading the charge. These innovative systems mark a monumental shift away from the traditional single-use rockets that dominated the space industry for decades. By enabling the recovery and reuse of launch vehicles, SpaceX has dramatically reduced the cost of access to space, making it more feasible to conduct frequent and sustainable missions. The success of this paradigm shift has set a new standard, pushing other companies and agencies to explore the potential of reusability in spacecraft design. In parallel with these advancements, propulsion technology is seeing major breakthroughs that promise to revolutionize how spacecraft travel through space. One of the most promising developments is the use of ion thrusters, which rely on electrically charged particles to generate thrust. While ion thrusters produce less thrust than traditional chemical rockets, they are far more fuel efficient, making them ideal for deep space missions where conserving fuel is crucial. These systems, already in use by several space agencies, offer a glimpse into the future of long-duration space exploration. Further down the road, nuclear thermal propulsion is emerging as a potential game-changer. Unlike traditional chemical rockets, nuclear thermal propulsion could offer a higher thrust-to-weight ratio, significantly reducing travel time to destinations like Mars. This could open the door to manned missions to the Red Planet, potentially within the next few decades, and lay the foundation for humanity's deeper exploration of our solar system. Advancements in material science are also playing a critical role in the design of spacecraft. The integration of lightweight composite materials and self-healing skins has proven essential in enhancing the durability and efficiency of spacecraft. These materials not only help protect spacecraft from the harsh conditions of space, such as extreme temperatures and micrometeoroid impacts, but also reduce overall vehicle weight, which is a key factor in fuel efficiency. As technology continues to evolve, these materials will only become more advanced, providing increased resilience to spacecraft as they venture farther from Earth. Artificial intelligence, AI, and robotics are also making significant strides, playing an increasingly prominent role in the design and operation of spacecraft. AI systems can now facilitate autonomous navigation, onboard decision-making, and even systems maintenance. This automation reduces the need for constant ground control intervention, allowing for more resilient and self-sufficient missions in the deep space environment. With AI at the helm, future missions can operate with a level of independence that was once unimaginable. Another exciting frontier in spacecraft design is the development of inflatable habitats and modules, with companies like Bigelow Aerospace leading the way. These innovative habitats represent a significant leap forward in creating livable spaces for astronauts. Unlike traditional rigid modules, inflatable habitats can be compactly transported and then expanded once in orbit or on another celestial body. This makes them ideal for long-duration missions as they can provide astronauts with a more comfortable and spacious living environment in the harsh and confined conditions of space. These habitats could be pivotal in supporting missions to the Moon, Mars, and beyond, offering a viable solution for human habitation on distant worlds. Together, these advancements in spacecraft technology are opening up new possibilities for space exploration. They are pushing the boundaries of what we thought was possible, making the dream of a sustainable human presence in space more attainable than ever before. With each technological breakthrough, humanity inches closer to the stars, ready to embark on the most extraordinary journey in the history of our species. Funding the future of space exploration, the ambitious goals of space exploration are made possible not only through technological advancements, but also through the growing diversity of funding sources that support these efforts. Space exploration has long been funded through government budgets allocated to national space agencies such as NASA, the European Space Agency (ESA), Roscosmos in Russia, the China National Space Administration (CNSA), and the Indian Space Research Organization (ISRO). These agencies have long been at the forefront of scientific research, satellite deployment, and manned missions, with government funding providing the backbone for much of the work done in the field. In recent years, however, the landscape of space exploration funding has shifted. Private companies such as SpaceX, Blue Origin, and Virgin Galactic are now playing a central role in the industry, contributing not only groundbreaking innovations, but also substantial financial resources. These companies are funded through a mix of venture capital, private investment, and commercial activities, such as satellite launches, space tourism, and contracts with government agencies and other corporations. The involvement of the private sector has introduced a new dynamic to the industry, driving competition and fostering unprecedented innovation in spacecraft design and mission planning. The collaboration between public space agencies and private companies is also becoming increasingly common, as both sectors combine their strengths for mutual benefit. Public agencies provide the necessary oversight and long-term planning, while private companies bring efficiency and flexibility and the ability to rapidly innovate. This synergy has led to some of the most exciting advancements in space technology, from reusable rockets to autonomous spacecraft and beyond. Additionally, international collaboration is a cornerstone of space exploration funding. Joint missions and shared projects between space agencies from different countries allow for the pooling of resources, expertise, and financial burdens. Projects like the International Space Station, ISS, stand as a testament to the power of global cooperation, with space agencies from the United States, Russia, Europe, Japan, and Canada working together to create a multinational research laboratory in low Earth orbit. This collaborative spirit is essential for tackling the immense challenges of deep space exploration and ensuring that the costs of such ambitious projects are shared among the international community. Emerging funding sources also include crowdsourced financing for smaller projects, as well as university and privately funded research. Public-private partnerships are increasingly common, allowing smaller entities to contribute to the overall space exploration ecosystem. These new avenues of funding have made space exploration more accessible, enabling a wider range of participants to contribute to the quest for knowledge and discovery. As space exploration continues to evolve, the blend of public, private, and international funding will shape the future of our endeavors beyond Earth's orbit. With unprecedented technological advancements, a wealth of financial resources, and a spirit of global cooperation, humanity is poised to embark on an exciting new chapter in the exploration of the cosmos. The next great frontier is within reach, and the journey has only just begun. The funding behind humanity's reach for the stars is as complex as it is compelling, driven by an intricate blend of national pride, scientific curiosity, and commercial interests. These diverse sources of financial support fuel a broad array of space exploration initiatives, from foundational scientific research to ambitious manned missions. Each investment reflects the multifaceted goals and priorities of the global community, whose collective ambition is to better understand and explore the vast, uncharted territories beyond our planet. However, with this expansion into space comes a new set of political challenges. As nations and private entities increase their presence and activities in space, the implications of territorial claims and resource exploitation are becoming increasingly significant. Space, once a frontier for pure scientific discovery, is now a competitive arena for geopolitical rivalry. This competition isn't just about prestige, it's about securing strategic advantages, controlling resources, and achieving scientific milestones that will shape the future of humanity's endeavors in the cosmos. One of the primary challenges in space governance is ensuring its peaceful use. The Outer Space Treaty, established in 1967, serves as the cornerstone of international space law, declaring that space is free for exploration and use by all countries. But while it prohibits the sovereignty of any celestial body by any nation, the treaty has not accounted for the rapidly escalating activities in space. The placement of satellites, the establishment of lunar and Martian bases, and the extraction of precious resources from asteroids and moons are all areas where tensions may arise. As space becomes an increasingly vital domain, the risk of conflict grows. The stakes are high. Who controls resources such as water, ice, or rare minerals could potentially shift economic and geopolitical power back on Earth. This reality raises profound questions. Who has the right to these resources, and how should the benefits be distributed? As these questions emerge, they may lead to new international frameworks focused on equitable resource sharing, environmental protection, and a shared vision for the future of space exploration. Yet, the political complexity does not stop there. The growing involvement of private companies in space exploration adds another layer of nuance to the debate. Once largely the domain of governments, space is now a new frontier for corporate ventures. This introduces the possibility that private entities may challenge traditional concepts of national sovereignty and authority in space. As these companies launch their own missions and establish extraterrestrial projects, they will inevitably complicate the existing framework of national representation in space. Should these companies be held to the same international standards as government-led missions? Should they have the same rights, responsibilities, and regulatory oversight? These new questions will require thoughtful consideration and innovative solutions from the international community. As humanity continues to expand its presence in space, we must navigate the development of governance models that ensure space remains a domain for peaceful cooperation, not rivalry. This might involve updating current treaties, forging new international agreements, and fostering dialogue between nations to create a balanced approach that combines national interests with a collective responsibility for space as a shared global resource. The future of space exploration hinges on how effectively we can balance national ambition with the broader shared vision of space as a place of mutual benefit. We must consider equity, sustainability, and the long-term environmental impacts of our actions in the cosmos. The political ramifications of how we manage, protect, and share the territories and resources of space will shape the trajectory of humanity's journey into the stars. As humanity's exploration extends beyond the Earth, the question of how international laws apply to space becomes more pressing. The governance of these extraterrestrial territories is akin to the establishment of a cosmic constitution. The Outer Space Treaty, a remarkable achievement of global cooperation, has been ratified by over 100 countries since its inception. It enshrines the principle that space shall remain free for exploration and use by all nations. But as space activities intensify, this treaty may need to be updated or supplemented to address the complex challenges of the future. The stakes are higher than ever before. As we venture farther into the cosmos, the political and legal frameworks that govern space exploration will determine not only the future of space itself, but the global relationships that define it. The coming years will undoubtedly require an unprecedented level of cooperation and foresight to ensure that space remains a realm of discovery, peace, and shared progress for all of humanity, but prohibits any nation from claiming sovereignty over celestial bodies. It also emphasizes that the moon and other celestial bodies must be used exclusively for peaceful purposes. This extends to the prevention of placing nuclear weapons or any other kinds of weapons of mass destruction in space. However, the application and enforcement of these laws in space present a complex challenge. Unlike laws on Earth, there's no global authority or enforcement mechanism in place to ensure adherence to these principles. As commercial space ventures and satellite launches become more common, the intricacies of space law and its practical implications will need to evolve, providing a fascinating intersection of science, ethics, and international cooperation. In the past decade, space exploration has seen extraordinary advancements. Among these, the Mars Science Laboratory mission stands out, with its successful landing of the Curiosity rover on Mars in 2012. Curiosity's ongoing exploration has provided invaluable insights into the red planet's climate and geology, hinting at past water flows and potentially habitable conditions. These findings have sparked new questions about the planet's history and its potential to support life. Another cornerstone mission was NASA's New Horizons probe, which made a historic flyby of Pluto in 2015. This mission delivered the first close-up photos of the dwarf planet, reshaping our understanding of the outer solar system. It opened a window into the mysterious world of Pluto, showing us landscapes we had never imagined. The European Space Agency's Rosetta mission also deserves mention. In 2014, Rosetta made history by landing on a comet for the first time. This groundbreaking achievement provided us with detailed data on the composition of comets, offering insights into the early solar system and the building blocks of life. These missions, alongside many others, have marked a decade of extraordinary space exploration. They have deepened our knowledge, sparked global interest, and ignited imaginations worldwide about the vastness of space and our place within it. In response to this surge in space exploration, educational systems around the globe are beginning to pivot. More and more, space sciences and technologies are being integrated into curricula, preparing the next generation for a future that increasingly reaches into the cosmos. This shift in education isn't just about teaching science. It's about fostering a multidisciplinary approach that blends mathematics, physics, engineering, and even biosciences. The goal is to equip students with the foundational skills and knowledge needed for space exploration and related technologies. Innovations in learning are playing a key role in this transformation. Virtual reality simulations of space missions, for example, are offering students hands-on experiences, allowing them to feel as if they're actually navigating through space. Educational partnerships with space agencies provide even more practical exposure to the world of space exploration. Meanwhile, universities are expanding their programs to include cutting-edge fields like aerospace engineering, like astrobiology, and planetary science. These initiatives aim to create environments that foster research and discovery, helping drive humanity's quest beyond Earth. Emphasizing critical thinking, problem-solving, and creativity, these educational endeavors are crucial. They prepare future astronauts, engineers, and scientists to navigate the challenges and seize the opportunities that space exploration will inevitably present. Through these efforts, the educational system is evolving, preparing not just to imagine a future in space, but to build it, but to actively prepare for it, ensuring the next generation is ready to contribute to humanity's next giant leap. Space exploration, while pushing the boundaries of human knowledge and capabilities, carries with it environmental impacts, both direct and indirect. One of the most pressing concerns is the debris left in Earth's orbit, commonly known as space junk. This debris includes defunct satellites, spent rocket stages, and fragments resulting from disintegration, erosion, and collisions. The growing presence of space junk poses significant risks to operational satellites, the International Space Station, and future missions. These risks could potentially trigger a cascade of collisions, known as the Kessler syndrome, which could create a chain reaction of even more debris, further endangering critical infrastructure in space. On Earth, the launching of rockets is not without consequences. The rocket propellants used in space missions release harmful substances like chlorine and alumina particles into the stratosphere, substances that can contribute to the depletion of the ozone layer. In addition, the environmental impact of constructing and maintaining sprawling launch facilities cannot be overlooked. These facilities often disrupt local ecosystems and wildlife, further compounding the ecological toll of space exploration. Despite these challenges, the space community is becoming increasingly aware of these issues, and there are concerted efforts underway to design more sustainable rocket technologies. Plans for debris removal and the development of international guidelines to minimize and mitigate the environmental impacts are also gaining momentum. As space exploration advances, the challenge lies in balancing the quest for discovery with environmental stewardship. The need for sustainable practices in our journey among the stars has never been more urgent. This delicate balance will define how we progress into the cosmos while safeguarding the Earth and its environment for future generations. Meanwhile, the future of the International Space Station, ISS, a symbol of international cooperation and scientific achievement, remains pivotal in shaping the future of space exploration. The ISS currently orbits Earth and serves as a microcosm for scientific and technological research in space. However, with its operational lifespan set to conclude in 2024, discussions are ongoing among the partner nations, the United States, Russia, Japan, Europe, and Canada, about extending the ISS's life until 2028 or beyond. As the ISS continues to age, maintaining its safety and functionality will require substantial investment. There's also growing interest in transitioning the ISS from a state-operated model to a more commercially driven one. Private companies are looking to utilize the ISS for research, tourism, and manufacturing, potentially paving the way for a new era of space stations. At the same time, several countries and private entities are expressing interest in developing their own orbital platforms, each focusing on specific scientific, commercial, or exploratory objectives. In the interim, NASA and its partners are setting their sights on the Moon and Mars, with plans to apply the knowledge and experience gained from the ISS to build sustainable outposts that can support long-duration missions. The legacy of the ISS, particularly in terms of international collaboration and scientific research, will undoubtedly influence future space endeavors as humanity continues to push the boundaries of exploration and reach beyond the confines of our planet. Advances in propulsion technology are also playing a crucial role in reshaping the landscape of space exploration. With the development of new propulsion systems such as ion thrusters, nuclear thermal propulsion, and even theoretical concepts like solar sails, the possibilities for space travel are expanding. Traditional chemical rockets, while powerful, are limited in efficiency and speed, making long-duration missions to Mars and beyond a daunting challenge. These new propulsion technologies promise to revolutionize space travel by offering higher efficiency and significantly reducing transit times to distant celestial bodies, making missions to Mars and the outer planets more feasible. Moreover, the ability to launch heavier payloads and conduct more frequent missions due to reduced costs could vastly expand our capabilities in space. This would allow for the construction of large-scale infrastructure in orbit and on other planets, as well as enabling detailed, comprehensive exploration of the solar system. As these advanced propulsion technologies continue to evolve, they may not only make the cosmos more accessible, but also open new horizons in our understanding of the universe and our place within it, heralding a new era of discovery and adventure among the stars. Humanity's future in space is full of possibilities, but it will require innovation, collaboration, and a commitment to sustainability to ensure that the stars remain within our reach for generations to come.